in a second. Okay, thanks a lot, Will. So it's 3:10 UTC. Well, morning, midday, evening, night, depending on where you are. So I guess we can get started now. Just get my intro slides up. Okay, great. So welcome everybody to our 3-day SAZERAC-SIP this time about learning the high redshift universe. Oh, and maybe at the beginning, I just ask everybody to mute the mix because we're live on YouTube now. And if not, I think William in the background and also the other SOC might just mute you and be that rude. So, but that doesn't mean you're not allowed to put questions, but we'll come to that in a second. So anyway, so very welcome to our SAZERAC-SIP for the next 3 days, afternoon at UTC. And here we have our SOC for this meeting, which are Isabella Carricci from the University of Turin, Pratika Dayal from Groningen, Emil Ishida from Auvergne, Adrian Liu from McGill University, Andrew Messinger from SNS Pisa, Stephen Murray from Arizona State, David Pellegrino from SNS Pisa as well, and Yuxian Qin from University of Melbourne. And our co-chairs for these 3 days are going to be Michele Bianco, Samit Giri, and myself, Caroline Hennecke from Hamburg Observatory. And well, let's get started, I guess, and just dive into the logistics. And while mentioning logistics, I also would like to thank very much Stephen Wilkins and also William Wilber, who's online and supporting us a lot in advance to this meeting, but also right now actually on YouTube. So for presentations, we'll be online on the Zoom Slack for live presentation, and you're also encouraged to ask questions either on the Slack channel, hashtag 22SIPML. If you're not a member there already, please join us there, as well as on Zoom. We encourage a little bit more to put questions on the Slack, because then we can keep track, and the speakers, they can interact with you and they can reply, and you can, well, carry the discussion on. But of course, if you have an urgent, spontaneous question, or you just want to naturally kind of pose it yourself to the speaker, please just raise your hand in the Zoom, and we will try to see you. If not, please also stop us and speak up if we totally oversee that. And well, if you go on the channel, you also find lots more logistics and info. So we have our SIP website tagged, the Zoom link again, GatherTown, I'll come to that in a second, and also for the speakers, we'd encourage you, you don't have to put your slides on the Google Drive link that's given there. So we can, yeah, keep track and admire your slides. And as well, of course, the YouTube channel, the YouTube link for our broadcasting these days, and the recordings when the meeting is over. And well, I mentioned the broadcasting. There's a playlist with the different SAZERAC-SIPs over the past ones. Always nice to tune back in. And well, that's it for our presentations. And for our logistics, for the scatters and highlights, well, we tried, modulo some time zone constraints and so on, to split the meeting a little bit up into more of a focus on the first day, which is today, on learning about high redshift galaxies. Then the second day, we're trying to focus a bit more on learning that's assisted with simulations. And day 3, we have an extra session that strives to be friendly for Asia Pacific Australian time zones, as well as a second session in the UTC afternoon, where we wrap up the meeting and well, end with a bit more focus on the turnout centimeter signal as well. So moving through there, we have today an overview introductory talk by Charlotte Mason on considering reionization and observation of galaxies, fitting the focus of the day. On the second day, we will have Francesco with Navarro with the role of simulations and machine learning and astrophysics, and we have Cav Trott for our Asia Pacific Australia friendly session talking about extracting information from Murchison Widefield Array EoR data. And what I would like to highlight here, besides our overview and introductory talks, are the flash talk session. This will be given tomorrow at the end of session 1, just before the break. So stay tuned for our 2-minute flash talks that will also highlight some interesting results. Also, if you want to interact with speakers, but also flash talk speakers, or generally other participants, feel free to dive in or join the gather town we have set up. And also what I would like to highlight lastly is our dedicated discussion session in the end of day 3, at the end of session 4, where we would like to summarize and incite a bit the discussion about, well, where the learning of the high redshift universe should go in the future. So your main places to go to are, well, besides Zoom, where we are now, also the channel where all the information should be tagged. If not, ping us and we will put it there, as well as a website where you can find the schedule. And I would like to highlight as well your contributions that came in. So this is a word cloud from the abstracts that came in that I couldn't resist putting together. So as you can see already here, we're quite data driven in the topics that we're going to look at the next 3 days. So partly observations, but also simulations. And then of course our 2 big kind of drivers, galaxies at high redshift and the Epoch of Reionization, are also highlighted here, and well, a wealth of methods and modeling that come along with it. And what I think is also really nice, as Stephen Wilkins, well, they started to propose this meeting also to help young researchers in these times to, well, get their work out there and be seen. So we have over 50% of students in our contributed talks. We have roughly a third of postdoc fellows, and that leaves a bit around 15% for staff and faculty. So I think it's really nice that we have many students, kind of a young and dynamic field. And well, let's see what they're going to tell us the next days. And to prime a little bit what's coming, just very briefly, as you all know, I'm sorry. This was too quick. As we all know, our highlight was going to be the high redshift universe, where we're mostly focusing on properties of high redshift galaxies, but also the IGM, other media, the cosmic 1 centimeter signal during the EoR, the Epoch of Reionization, and cosmic dawn, as well as, let's say, the transition period between reionization and the universe that starts to look more and more like our present day universe. And I think it's just now very exciting times to, well, push this frontier to higher redshifts and learn about the high redshift universe with large-scale surveys and high-resolution studies, starting with precursors or being just around the corner and waiting for us. So I'm sorry if I didn't put all the experiments here, so this is many more, of course. But what I'd like to say with that is that we kind of need to or want to strive in the next years to extract more and less biased information, basically mine this wealth of data that is lying there for us. And also a bit like in particle physics, where already for years people are using stuff like triggers, and they can't basically store all the data that reaches them or that it generated in their colliders. And we're kind of entering this era as well, where we need efficient data reduction automation to deal with data, kind of entering a data-driven regime, where, well, for example, the ability of some machine learning methods or modern machine learning to increase its performance with an increasing amount of data comes in very handy, as well as like other properties like representation learning, the ability to kind of read from the data what's needed to answer the question posed. So these are things that kind of push new types of machine learning, which is also quite visible on arXiv if you look at the number of studies that are put there that mention different variants of machine learning over the last couple of years, where it's like very, very much accelerating since like 3 to 4 years or 5, you know. And I just would like to remind for those who were there, but also for those who weren't, that this actually kind of picks up a discussion we had at the SAZERAC-SIP last year, or almost exactly 1 year ago, at the 21 centimeter SIP, where we finished by discussing very much the machine learning part of the meeting, with kind of a range of questions that focused on actually when does machine learning really improve over traditional methods. And traditional methods means like, of course, MCMC we've been using extensively and so on. And what needs to be actually done in the next couple of years in terms of methods or architectures, if we talk about deep learning, to make those a reliable scientific method or reliable scientific methods, regardless of their reproducibility, but also their interpretability, like what people call the black box sometimes for some of the, let's say, larger parameter algorithms. And also basically the big question for supervised algorithms, how do we train them versus actually how can we make them more independent maybe, and what's our ground truth, which is connected to how do we train them. And then the big question that concerns a good calibration of uncertainties and how do we get reliable posteriors with new methods that go beyond MCMC. But actually this meeting kind of brings together those things. So we have MCMC, we have statistical learning, we have machine learning, deep learning, all of these kind of coming together right now to tell us about the high-redshift universe. So to wrap this up, we have, well, basically our simulations, observations that try to inform us about IGM and source properties at high redshift, concerning reionization history, remove contaminants like foregrounds, etc., and also to detect single sources and features still. And well, they are kind of using anything from classical learning to machine statistical deep learning. And I think this meeting will be very interesting to pick up on these questions from last year, where basically we were looking at the questions I posed here also in the end of the meeting, and kind of just to move on from there to see what has happened in terms of potential improvement of new methods, what methods have proven to be useful or should be tried also in the future, how are we working on the reproducibility and interpretability, has there been some progress, do we still need to work hard on this or not, ground truth, supervised, not supervised learning, and of course the big question of uncertainties. So yeah, so let's survey the landscape of machine learning based approaches for studying the high redshift universe. And this is where we get started now with our first introductory overview talk by Charlotte Mason, constraining reionization from observations of galaxies. And Charlotte is a professor at the Dawn Center at the University of Copenhagen, and well, I hand over to her for the screen sharing.
Okay, thanks. Let's see if I can figure this out this time. Okay, is that working?
It is there. And yeah, maybe for all the speakers also, for now and for later, so we'll try to give a roughly 5-minute warning towards the end of the slot to kind of keep you posted.
Okay, well, as I said, I can't actually see any of you, so you're going to have to just give me a verbal warning. Yeah, so firstly, thank you very much to the organizers for setting up this conference. I think it's really timely. And I'm certainly really excited to learn about advances in learning about the high-redshift universe. I guess I should state that probably most of what I'm going to talk about here is the like classical learning. I guess at this point I'm a dinosaur, so I'm really excited to hear about what younger people are doing. And obviously, thank you very much for the invitation to speak about constraining reionization from observations of galaxies. And I put the star around galaxies because I'm also really going to talk about quasars too, so things inside galaxies. And so I don't really need to introduce this very much. I think Caroline already did a really nice job of this, but essentially, when we're looking at reionization in particular is intrinsically linked to the properties of the first stars and galaxies. And so by understanding how reionization happened, we hope to learn something about those first stars and galaxies. And I think we're really, I think one of the reasons why this conference, the SIP, is so timely is because we're really at the edge of kind of an observational horizon. So obviously at the moment with the Hubble Space Telescope, we can observe galaxies sort of the end of reionization around redshift sort of 6 to 8. But new facilities that will be are in place right now. I think it's the first time I've given a talk since JWST launched. Will be able to directly observe both the galaxies and the IGM during this epoch of reionization and cosmic dawn. So I think it's really the right time to really consider the best ways to learn from these observations. And I think, at least for me, some of the really big questions that we can try and answer when we study the early universe is, I think in some ways understanding reionization and cosmic dawn is kind of the ultimate test of our understanding of baryonic physics. We really want to understand how the very first galaxies formed and what their properties were, and also what is the structure of the IGM on small scales. And so I think I'll try and argue that we can try and answer some of these questions by studying the timeline and the morphology of reionization. I'm mostly today going to focus on the timeline. And, I like to make this analogy that reionization, the reionizing universe is like this kind of bubbly loaf of bread. And why does it look like bread and not like a cake? Well, it's the ingredients that you put into it. And so in just the same way, the properties of these ionizing sources, the ingredients, will shape the structure of the ionizing IGM. And so what do I really mean by timeline of reionization? So really this means when and how quickly did the universe reionize? And so here I'm showing you this plot of the volume average fraction of neutral hydrogen in the universe as a function of redshift. So going back to high redshift early times, is a very neutral universe. And this reionization timeline is really most sensitive to the sort of total integrated emission from reionizing sources. And so there's a kind of a few things going on here, but the main things I want you to take away are that these white points, which are observational constraints, and this is pretty out of date, but I will show you the latest constraints towards the end of this talk. Basically, up until about 5 or 6 years ago, most of these were just limits, and there's not very many of them. But I think we've actually made quite a lot of significant progress in the last few years on building up this reionization timeline. And at the same time, we have these different colored lines, which are different simple models for how reionization might occur, depending on the properties of reionizing sources. And so, as I said, this is really sensitive to the sort of total integrated emission from reionizing sources. And so, for example, if you had a universe where you had lots of very low mass galaxies, so for example, a very cold dark matter universe with a very efficient star formation, then you would have reionization histories that look more like this purple one, where reionization can happen earlier. And that will be balanced out then by, for example, how easily ionizing photons can actually escape from galaxies and ionize the IGM. And if that process is very difficult, then that will tend to push reionization to later times, and you'll get models more like this blue one. But clearly, it would be great if we could get some more measurements of this reionization timeline in order to help better constrain the models of reionizing sources. And so in this talk, I'm really going to go over kind of three things. So the first is I want to introduce some of our observables. What do we have in order to learn about reionization? I'm going to talk about then how we can learn about reionization in particular from Lyman Alpha transmission, and this is mostly using Bayesian approaches. And then I will review some of the sort of recent results and discuss some of their limitations and then some of the future prospects. And so what are our observables, these high redshift, to explore the high redshift universe? And so, of course, the first thing are the sources themselves. So we have observed hundreds of galaxies at redshifts greater than 6. And this is mostly due to large observing campaigns with the Hubble Space Telescope. And so what you're seeing here is the luminosity functions. So the UV luminosity, the number density of galaxies is a function of their UV luminosity and redshift. But our information here is still quite limited. So in particular, we can only, we're really kind of reaching the observational limits of Hubble. One, we can't see any higher in redshift. Obviously, James Webb will help with this. But we hit a luminosity limit. We just can't see galaxies fainter than a certain limit. But we think we're really only seeing the tip of the iceberg. There should be a much larger population of very faint galaxies out there. And we don't really know what their role is in reionization. As well, we also don't know anything or don't know much about the ionizing photon output of these galaxies. Particularly because above a redshift of about 4, we actually just can't observe the ionizing part of these galaxies' spectra. We can only observe the non-ionizing UV continuum. So we just don't know in terms of ionizing flux what these galaxies are putting out. At least we can't measure it directly. So there's a lot of uncertainties here. I'll also point out that I'll talk a little bit more about quasars later. Just for those of you who don't think about this very much, quasars are kind of at the bottom left of this plot. They're really thousands of times rarer than galaxies. And if you have this kind of, the simplest level, really, reionization is just a balance between ionizations and recombinations in the IgM. And so we can write this as a differential equation where the ionization, the sources of ionization, we have this term n.ion, or the number density of ionizing photons. And this is really just the number of galaxies that exist, the amount of ionizing photons that they produce, and the fraction of the ionizing photons which escape the ISM and can ionize their surroundings. And I think, as I said before, really the thing we probably best know is the number of galaxies, but that's still not 100% sure because we don't know what happens to very faint galaxies. But we can describe all of these things basically by using parametric models, for example, models that are functions of halo mass, and come up with kind of simple prescriptions for how reionization might occur. And obviously, most of the time often when this is done, you can do this by kind of assuming a homogeneous reionization. So taking this equation and applying it to the entire universe. But then on small, if you want to do this sort of properly, you would obviously want to model it in a spatially varying way. So for example, every cell in a simulation would follow this type of equation. And another important thing to consider here is also the recombination rate. So this is really determined by the structure of the IgM. So for example, the clumpiness of the IgM. And I think is something that is often a bit underappreciated, but can have important implications for how we think about reionization. And so basically what I'm going to really talk about today is actually constraining the rate, so the time evolution of the ionized or neutral fraction as a way to hopefully understand these inputs, the ionizations and the recombinations. And so, obviously, I think we'll hear some more talk. We'll hear a lot more talks about this, especially on Friday. We can observe the neutral gas directly using 21 centimeter emission, But I'm really going to talk about how we can observe the imprint of the neutral gas on the spectra of distant astrophysical sources. So essentially just shining like a really bright light through the IGM and observing the imprint on distant object spectra. And this is a technique called Lyman Alpha tomography. And we can do this with galaxies, quasars, gamma ray bursts, etc. And so a very brief review of Lyman Alpha. So Lyman Alpha is produced really ubiquitously in young star-forming galaxies and in quasars. It's the 2-to-1 transition in neutral hydrogen, rest frame wavelength of 12-16 angstroms. And so, for example, this is a spectrum or a stacked spectrum of a young star-forming galaxy with this booming Lyman Alpha emission line. Of course, when we go to higher redshifts, these observations become much more difficult to make. So this is an example of Lyman Alpha emission at redshift of 7, where we have very noisy spectra, or kind of at the sensitivity limits of the largest optical and near-infrared telescopes on Earth. And I'll talk a little bit about some of the ways that we have to kind of account for the noise in our data a bit later. And the great, or maybe annoying thing about Lyman Alpha is that Lyman Alpha photons have a very high cross-section for scattering of neutral hydrogen. And so that means we can use them as a tracer for the evolving IGM. So this is the Lyman Alpha cross-section. And the two important things to notice are this very high peak at the resonant wavelength. And this is what gives rise to the Gunn-Peterson troughs that I'll talk about a bit more in a minute. And so an important thing to notice here is that because this cross-section is so high at resonance, it actually doesn't take very much neutral gas to be completely optically thick at resonance, so only a fraction of about 10 to the minus 4. During reionization, what becomes very important is this damping wing absorption. And this is really gives you information about neutral gas or very neutral gas of order sort of 0.1 to 100 or 10% to 100% on large scales. And as I described, we can then use these astrophysical sources as backlights. So I'm just going to show you a quick kind of cartoon movie of what that looks like. If you have a high redshift source, so here's a quasar, as the light from that quasar redshifts as it travels through space towards us, every time it encounters neutral hydrogen gas, if the light blue wood of Lyman Alpha is redshifted into the resonance, it gets absorbed. And so this is what we call the Lyman Alpha forest. And so this has been one of the key indicators of an increasingly neutral IGM. So if you can see this compilation of quasar spectra here from FANA till 2006, if you look at the lowest redshifts, so redshifts just below 6, we can see a lot of structure in this Lyman Alpha forest telling us that Lyman Alpha flux is transmitted. There can't be too much neutral gas. But at higher redshifts, redshifts be above 6, we start to see a lot of gaps in the Lyman Alpha forest, and these Gunn-Peterson troughs, which tell us that there has to be a significant amount of neutral gas at these redshifts, or at least I said it has to be above about 10 to the minus 4. And in terms of sort of more quantitative measurements that we can make from these spectra, so there's two sort of real metrics that people use. So the first is called the dark pixel fraction, or the dark fraction, or dark gaps fraction. And this is really the fraction of this quasar spectrum that is dark. And that enables us to put sort of pretty much model independent upper limits on the neutral hydrogen fraction, x sub h1. And that's because basically, in order for these regions to be dark, there must be neutral hydrogen. And the other observable or sort of metric that we can use is the effective Lyman Alpha optical depth. So you can calculate effective optical depths to Lyman Alpha in different regions of these spectra and create probability distributions. And those can be then compared with simulations and have been used to constrain the neutral hydrogen fraction and properties of ionizing sources. Then during reionization, as I said, or late, in towards the kind of the mid stages of reionization, as I said, we really need to consider the damping wing. And so the damping wing is a smooth attenuation of flux on the red side of the line that depends on the proximity of the source to a neutral region. So here you're seeing some sort of cartoon with galaxies at different places inside and outside of an ionized bubble. And you'll see that if you look at the different spectra along the bottom, the gray lines, so here we're assuming that all of the galaxies emitted the same Lyman alpha flux and the same with the same line shape. So all of these gray dashed lines, they're all the same galaxy. But you can see that the observed spectrum that we would actually measure is very different coming from each of these galaxies. And that's because it depends on where the galaxies are inside the reionizing IgM. And so we want to be able to use this technique to measure properties of the IgM. And a key observable in the last few years has been to look at the fraction of galaxies detected with Lyman alpha as a function of redshift. And what we're observing is that above about a redshift of 6, this fraction declines pretty dramatically. This is seen in this Lyman alpha fraction. Really, we also see this in the distribution of Lyman alpha equivalent widths, which I'll come to in a minute. So it's a kind of more smooth attenuation of Lyman alpha flux rather than we see some rather than it kind of being a bimodal thing. And we can also see it in the Lyman alpha luminosity functions. And so now I'll move on to how we can actually extract information from these types of observations. How can we learn about reionization from this Lyman alpha transmission? And I'll describe a Bayesian approach that I and several others have taken to do this. So essentially what we're trying to do is recover the damping wing transmission. And we want to be able to do this by, we have some observed Lyman alpha spectrum. So this example here is actually a quasar, so you can actually see the effect of the damping wing. And so the black line here is the observed spectrum. We can then come up with some model for the intrinsic emission, which is this red line here, which can be reconstructed in various ways. So here, using a model that's based on the continuum redwood of Lyman alpha. And then what we want to be able to do is to take the ratio between the intrinsic and the observed spectrum, and that tells us about the Lyman alpha transmission or the damping wing absorption. And then we want to be able to use that to measure something like the neutral fraction or eventually other properties, source properties of reionization. So how do we do this? How do we connect our Lyman alpha observations to the neutral fraction? And so if I want to put this in a sort of a Bayesian way, what I want to know is what is the posterior distribution for the neutral fraction given our observations. And so the example that I'm going to talk about now, we're considering galaxies that emit or maybe don't emit Lyman alpha emission. And so in our case, the observables are Lyman alpha equivalent widths and some other properties of the galaxies that we can observe. So for example, UV magnitudes. And so using Bayes' theorem, we can then write this down as the product of the likelihood for observing a galaxy with that equivalent width, given the neutral fraction and the other galaxy properties, times the prior. And then an important step here is that because reionization is so inhomogeneous, you can't write this likelihood down analytically. And so what we actually want to be able to do is sample all of the different spatial variations that these Lyman alpha photons might have to deal with because they're coming along all of these sight lines through different reionizing bubbles, etc. And so what we can do, or what we have to do really, is forward model this likelihood. And so to do this, all of these approaches have essentially been to embed models for Lyman alpha emitting galaxies or quasars into larger scale reionization simulations. And so in order to forward model the observed Lyman alpha properties in which you could then directly compare with your observations. And so, for example, here, certainly what I have done is use simulations from 21 centimeter fast at different neutral fractions, and then populate halos within those simulations with realistic galaxy properties. So UV magnitudes, intrinsic Lyman alpha equivalent widths, and some parameters that tell you about the line shape of Lyman alpha. Of course, all of these properties are not just sort of one-to-one relations, but they're actually drawn from distributions. So there is obviously scatter in what we observe in these galaxies, and that needs to be accounted for. And a lot of these properties are also dependent on other galaxy properties. So most of these quantities then become conditional on, for example, the halo mass. And then finally, we can calculate the transmitted fraction of Lyman alpha photons, which is an integral of the line shape of Lyman alpha and the optical depth through the IGM. And this thing, I should say, is actually pretty computationally challenging. So in order to get the optical depth itself is basically an integral. You have to add up all of the contributions from neutral gas along every single line of sight. And then you have to do an integral over it, including all of these different sample properties. So I'm very curious to know if there are, hopefully maybe I can have some discussions about ways that we can maybe use machine learning to kind of speed up some of these parts of these kind of traditional learning problems. Once we have these transmissions, Lyman alpha transmissions, it's quite informative to look at those too. So here I'm showing you probability distributions of the Lyman alpha transmissions. Going from the left to the right, the IGM is becoming increasingly neutral. And you can see that the transmission decreases pretty rapidly when the universe is very neutral. We don't expect to see very much Lyman alpha. But obviously this is then still a broad distribution, and that's because of the sightline variation, because reionization is so inhomogeneous. Another thing that's important to note here is that this also depends on galaxy properties. So in particular, we find there's quite a big difference between UV faint, low mass galaxies and UV bright galaxies, high mass galaxies, because these bright galaxies probably live in dense and early reionized regions, so they have a higher transmission. And I think in doing these types of Bayesian problems, it's really important to bring your likelihood as close to the data as possible. And so what that means for us is actually we're really creating likelihoods that are for the spectra themselves, and especially because most of the time we don't even detect Lyman alpha. So we need to use the full spectrum in our likelihood. And that also enables us to do things like marginalize over photometric redshift, because often if we don't detect Lyman alpha, we don't necessarily know that these galaxies are at some redshift. So we want to use information from the photometric redshift distribution and other things that we don't really know, like the line width of Lyman alpha. So for example, if the line was very broad, we wouldn't have detected it because it was low signal to noise, but we can marginalize over all of those things. And so in the last few minutes, I just want to give you a kind of review of some of the results and then talk about some of the limitations and prospects. So the important thing, I guess, is the updated reionization timeline. And so this is the most up-to-date version, I think, now from a paper by Patty Boland that was on arXiv at the end of last year. And so you can see we've really, in the last few years, filled in this reionization timeline. So the orange stars here are measurements using the Lyman alpha flux or equivalent width distribution that I was just describing. And the gray diamonds are measurements of the damping wing in individual quasars, which is a very analogous approach. And I'm not going to talk about that. And so the implications of this, what we've observed in this reionization timeline is a fairly late and rapid reionization. And so there's some interesting implications for this. I think in the past, we considered that reionization, because there probably are all of these very ultra-faint galaxies, they did reionization. But actually, reionization happening so late maybe alleviates some of the need for lots of ultra-faint galaxies to contribute to reionization, and maybe imply a more rapid buildup of photons. And so there's kind of a debate, emerging debate about which galaxies contributed most to reionization, whether there are rarer, brighter sources, whether there's only a sort of certain population that dominates the ionizing photon budget, and also recent observations of a short mean free path of ionizing photons suggest that there are very strong sinks in the IGM, which actually would require a stronger contribution from faint galaxies. So this is definitely not a solved problem. I think we need to improve our models for ionizing photon production and escape in some of our simulations. For example, I think some of the models that people are posing here are not, basically, we know that F escape is probably not constant, and it may not really be a smooth function of halo mass. So it would be good to have models that are more flexible when we do these types of reionization inferences. I think a key thing here will actually be making measurements of the reionization morphology, because that will enable us to break some of these degeneracies by studying, because we know that the spatial fluctuations of the spatial variations in during reionization are quite strongly determined by the clustering properties of reionizing sources. And I'll just say then that I think some great progress has been made using these parametric models to understand reionizing source properties, particularly using very flexible models like this example here from a recent paper by Yusang Kin, using the parametric galaxy formation model in 21 centimeter fast. So you can...
So they're 4 minutes.
Yeah. So you can infer different properties of reionizing sources, for example, ionizing photon escape. And a powerful thing here was actually combining observational constraints in the likelihoods. So using information from the UV luminosity function and the dark pixel fraction, the Planck optical depth, and also the Lyman Alpha forest PDFs. Just one very bit of shameless advertising is that if you want to forecast parameter uncertainties in these types of parametric models, Fisher matrices may be a much more efficient way to do that than sampling a posterior, and can produce comparable parameter uncertainties to MCMC. Well, at least we've tested this for 21 centimeter observations. So you can look up 21 centimeter fish, which is a Fisher matrix wrapper for 21 centimeter fast. And basically, this is a kind of like a shopping list of at least things we've done and things that I think is still to do in these types of analyses. There are lots of uncertainties that we've been able to marginalize over, but I think there's still a lot of missing physics, and we need to understand, what are we missing in these types of models? What are the most important things that we need to add, and how can we do that efficiently? I'll say one final thing, which is that JWST will be observing a lot of relevant targets early in its lifetime. So these are some surveys that will be done in cycle 1, aiming to target early reionized regions and measuring Lyman Alpha and Lyman continuum escape. And I think we really need to be ready to interpret these types of observations, in particular, taking into consideration the very small field of view of James Webb compared to the typical sizes of ionized bubbles. And so I'm just going to end by leaving up my conclusion slides, which is that we have observed lots of high-redshift galaxies, but probably only the brightest ones, and there's a lot about them that we still don't understand. We can use observations of galaxies and quasars, measure the damping ring absorption of Lyman Alpha to learn about reionization, and we're finding that the IGM is pretty quickly becoming ionized between about redshift 6 to 8. But there's still a lot of open questions, and I hope these are things that we can start to discuss during this conference. Really, what's the best parameterization to use if we want to learn about the high redshift universe? What are the most important things we actually want to measure? And how do we efficiently include the important physics in these models, especially when there are so many things that we don't understand? How can we do that in a flexible way? Thank you.
Thank you very much for a nice overview. I'm just scrolling over the participants to see if there's a raised hand already. So please don't be shy and just raise your hand if you didn't make it to type on the Slack in parallel. Just checking the Slack. There's applause. If not, in the meantime, well, people can Slack. Oh yeah, I see Sambit has a question, a raised hand. Please.
Very nice talk. I was just had one naive question. When you said you forward model your to analyze Lyman alpha observations, do you do some approximate Bayesian inference, or you calculate an approximate likelihood?
We calculate a likelihood, which I'm not sure if this is the most robust thing that has ever been done, which basically calculated by sampling. We sample from the simulations to get the transmissions, and then create a smooth model by basically using a Gaussian kernel density estimator to make a smooth likelihood. I think doing some kind of approximate Bayesian computation probably would be a better way to do this. I think when I wrote this out, that was not what I was thinking of. I mean, I think I started reading about it and then I got lost. But if people have, if that seems like a faster way to do things, I'm definitely curious to hear how we can make this better.
Thank you.
Thanks. Yeah. So I see we have a question on the Slack by Carol, was the first one. Do you want to put it yourself?
Okay. Yeah, thanks. Very nice, good talk and very good overview. I was thinking, I couldn't really see the scale on your simulation snapshot, but I guess it's fairly large scale. So this means you're not resolving the small scale density fluctuations in the intergalactic medium very well. And yet they can be quite important for the Lyman alpha transmission. So how do you deal with that? Do you have an extra modeling component there, or?
Yeah, that's a really good question, and I can't remember if that was on my to-do list, but I think that's probably one of the most important to-dos, because I completely agree. I mean, so the simulations that we use at the moment contain, I mean, the resolution is basically 1 megaparsec, which is not sufficient to resolve this kind of smaller scale fluctuations around galaxies. At the moment, we have a very crude approximation where we basically cut off all flux within the circular velocity of every halo, which is kind of like assuming that that's kind of the CGM effect, but it's very crude. But I think this is really something that would be great to include, maybe, for example, by kind of patching on, I know that Andre has done this previously, kind of patching on hydro simulations to capture the smaller scale physics. But again, trying to do this in an inference framework becomes quite challenging because you need, stitching together lots of things that you then need to integrate over and then sample over is a challenge, but yeah.
Okay, thanks.
So we are using the buffer right now, but I think this is okay. So we have another maybe quick question on the Slack. Baron Mighty, if you want to pose it yourself, please go ahead. If not, I will read it.
Yeah, am I audible?
Hey, yeah.
Yes, very nice talk. So I was wondering what's the motivation behind using the Fisher matrix approach you have mentioned in the last few slides, I think. So over the full MCM. So is it only the efficiency thing or anything else?
So yeah, that's a good question. I'm sorry I didn't really have much time to talk about that. Mostly, I mean, I guess it's efficiency. But it means that you can do it becomes very easy to explore much larger parameter spaces. So for example, with 21 centimeter fast, like 21 MCMC, there's, I can't remember what the biggest number of parameters that's been explored is. It's something of order like 11.
Okay.
Andre?
It's 9.
9, okay. And obviously with a Fisher matrix, it scales as, I think it's 2n plus 1 the number of parameters is the number of simulations that you need. So you can do like 20 simulations or 20 parameters really quickly. And so the motivation for this was actually we're trying to add in some additional parameters to 21 centimeter fast to explore dark matter models, and we just wanted a quick way to do it rather than having to run an MCMC, and this seemed like a good way, and it seems like it works, which is good. It's comparable to an MCMC if you want to do parameter forecasts.
Thanks.
Okay, so thanks a lot again to Charlotte for the nice introductory talk. So we move on now to the contributor talks, and we'll start with L.Y. Erin Young, talking about paving the way for JWST. So that fits nicely on where Charlotte was ending, I guess. So it's yours.
Thank you so much. I want to thank the organizers for organizing this. This is great. So hi, my name is Erin. I am from NASA Goddard Space Flight Center, and I'm going to present today is not really work that has to do with machine learning, but the hope is that these predictions will help us pave the way to an exciting decade of using JWST enrollment to study the high-redshift universe. And also, hopefully, maybe some of these simulated data will become someone else's training set or my own. Who knows? Okay, so previously, for a few years, I have been working on a series of work called the Semianalytic Forecast for JWST. And I'm not planning to go over all the results from paper 1 through 5, but just to quickly recap, I put together a modeling pipeline that is centered around the Santa Cruz semi-analytic model. And I use it to make predictions for quite a large variety of physical and optical properties for galaxies, and also for how these galaxies evolve at high redshift. So in paper 1 and 2, we looked at the physical and observable properties of galaxies. Paper 3 and 4, we explored the ionizing photon emissivity of these galaxies and how they can impact the intergalactic hydrogen reionization. So if I knew what Charlotte was going to talk about, I probably would spend a little more time on these two papers. But the bottom line is, I think the contribution for galaxies really went from dominated by low mass galaxies at the beginning of reionization, but that gradually transition to the more massive and brighter galaxies towards the end of reionization. And in paper 5, we managed to add contributions from AGN and their impact on helium reionization as well. So if this is your first time hearing this series of work, if you find any of these things interesting, please feel free to reach out to me and I can tell you more about these previous paper. And all of these predictions are done in a self-consistent semi-analytic framework. So you'll see more about it in just a bit. But the bottom line is it is really, really fast. We're talking about processing millions of halos overnight fast. So I'm really excited. Okay, so here, let me flash some of the key results for galaxies specifically. So what you're looking at here is the set of observations that our models are calibrated to. Blue is model output and everything else is observations. And the free parameters are calibrated here once at redshift 0 to try to match these observed constraints as much as possible. But what is really surprising is at redshift 4 and above, this model can reproduce the evolution observed by from high redshift observations. So this is the distribution for stellar mass. This is stellar mass function. And then here is the star formation rate function, and then a UV luminosity function, assuming a certain amount of dust. So we did not retune the parameter to make this work, but the fact that it works at reproducing these observed constraints is really exciting. And of course, we take advantage of the wide dynamic range of the SAM, and we go in and make predictions for also galaxies that have not been seen with current generation instruments. So hopefully JWST will be able to tap into these fainter galaxies and put constraints on them. So the Santa Cruz SAM is a model bundled a large collection of key physical processes that went into galaxy formation. So this is just a schematic diagram that gives you a sense of what is in the model and how these things are processed. Starting from a dark matter halo, we have hot gas and then cooling and then gas partitioning and then star formation, supernova feedback, and a lot of things. But honestly, there are quite a few things going in there. So the bottom line is the whole modeling pipeline is very modular. So we can easily do experiments by switching something on and off, or try different physical prescription for certain things, or rerun the model with different sets of physical parameter. And we have done this experiment before. So as a result, this pipeline gives us a good collection of physical properties predictions, such as the standard stuff, star formation rates, stellar mass. And then also we forward model these physically predicted galaxies into synthetic SEDs, and then we can calculate the observed infrared magnitude. So this is how these predictions are done. Okay, so this is what I've been building up for. The past predictions for paper 1 through 5 are more, for discrete redshift. They're efficient, flexible, but not exactly the most useful things for planning observations. So what happens in our next and last final paper for the series, paper 6, is that we put these predictions into a light cone format. So this is what it looks like, the data from a side view. So this is all predicted galaxies, but from a side angle. So with their physical location. So basically we take a dark matter light cone that is with halo sourced from a cosmological simulation, and then we put in SAM galaxies to it, the already calibrated tested model, and we put it into a light cone. So this is what it looks like. So this light cone spans from redshift 0 to 10, and with physical positions and locations kind of preserved from the cosmological simulation. So these galaxies are not randomly distributed. They actually contain clustering statistics. I can't show you any of those now. I can say that they match observations quite well from down to redshift 0.2 up to redshift 7. So yeah. Okay, so that was the data. And let me keep going with some demo. This is the Hubble UltraD field. We know this very well. And this is the simulated field, because now we have a light cone, so we can emulate what an observer sees in the sky. And I could have tweaked the color scheme to make this two look more similar, but I didn't do that. But just a bottom line, the color and size of data points are sort of scaled to the UV luminosity, rest frame UV luminosity. So they are somewhat comparable. But so also both sides apply similar limits to matching Hubble detection limit. But here is the same field. Now I put in all those JWST galaxies, and we can already forecast how well JWST will do in its, in future observations. And let me enlarge this small region to help you see the difference. And you can see we going down in rest frame UV luminosity, we're getting more of these low mass galaxies. And we can't wait to have JWST actually detect these galaxies. But meanwhile, if you want to grab the data and work with it, the mock data, you can do that already. Okay, so this is another view of the light cones. So basically I slice them and I give you 9 sample slides just to show you what is in there. So as expected, the lower redshift galaxies, the lower redshift slides has more massive galaxies and they're denser, and then at high redshift, I think I applied a magnitude cut. So there are fewer galaxies up there, but just for example, just to give you an example how this data set can be used. So here's one real life example. This is one group that I work with. This is the Cosmic Evolution Early Release Science Team, or SEERS, which is one of the JWST Early Release Science program. In their planning of the pointings, one of these light cone was used, and then we're able to optimize the pointing with this multiple instrument parallel mode, and of course get a sense of what we will see in the future. But I also want to point out that the data release for SEERS is now available online. So if you want to go check them out, besides the base catalog, we also have mock images and other data product as well. So this is available today. You can check them out. And I also created a deep cone. So this is much smaller. The last cone you saw was about 782 square arc minutes. This is much smaller. This is only 132, but it overlapped with the Hubble UltraD field. So the idea is to basically switch out the base cosmological simulation and create a smaller light cone, but at much deeper depth. So contain more lower mass objects. And this was used for the planning of the accepted Cycle 1 project, Cycle 1 program called NGDeep. So one example here is, I want to show you on the right. We have a mock image made for Sears using the Sears cone, and then a mock image for NG-deep using the new NG-deep cone. And you can see that, yes, there are more objects as expected, but well, the physical model was really behind all of these mock images that fuel what is in there. Yeah, great. Okay, so let's orient ourselves again with the Hubble UltraD field. And the next thing I want to talk about, the last thing, is the next big thing, Roman Space Telescope, which is the next big thing with a big field of view. Get how many minutes left?
So 5 minutes for Roman.
Thank you. Okay, so this is the Hubble UltraD field is in the little red box. You can keep an eye on that. I will keep that in there for scale. But I also highlighted the Roman field of view in this green box region. So let me quickly show you. These are the fields from past candle surveys. And these are the fields of my simulated light currents. So I made a field of them for candles, but they're not big enough to serve Roman, because I can't just tile them up. The large scale structure won't be right. So I went the opposite direction. Instead of making a smaller, deeper light current, I create a bigger one, a 2 square degree light current. And that contains, again, a lot of galaxies down to the resolution limit of the same as the candle light currents, but also with a large scale structure from a bigger box cosmological simulation. It is exciting. So Roman Space Telescope is not going to fly until 2027. And so I was getting in touch with the biggest program in JWST. I told them, we have these big light currents. Can we find some way to use it? And it turns out that Cosmos Web is going to survey 0.6 square degree of the sky, and they will reach depth at out to 27.5 to 28, which is pretty much exactly everything I want. So we'll get some real clustering statistics from this survey, and we'll be able to test them against these light currents. And I didn't just make 1 2 square degree light currents. I went out and make 5 of them. So each of them is 2 square degrees, 5 realizations total. So it contains over 60 plus million galaxies in total. Every one of them, I saved the full star formation history and high resolution spectra. So a total of 7 terabyte data. They will be released this spring. I can think of a lot of use case, machine learning or classical study to play with them. But of course, if any one of you are interested in exploring this big data era ahead of Roman, LSST, or Euclid, you are free to play with these. So the last minute, I just want to do a quick demo. So you can already access this data today. You can go Google Flatiron Institute Flat Hub, and then underneath you can find the Santa Cruz SAM. And then in there, you will be able to make quick plots just with a few easy steps. You can change the plot type, change the axes, and then pick a field, and then you'll be able to plot the data and only download the galaxies that you want to play with. You don't have to download all 7 terabytes at once, because who does that? But after you make some plots, or you selected what galaxies you want, you can just download the ones that you like to look at. And I'll leave you with a conclusion. Thank you.
Thank you very much. So I think we have time for 1 or 2 quick questions. So I don't see a hand raised yet. If you do, just you want to just speak up on the Slack. I don't see one yet. So in the meantime, I actually was wondering, seeing this really crowded kind of fields, I mean, amazing amounts of data. But I was wondering, is blending actually how much does it affect what you like to maybe derive from the fields?
So right now we did not treat blending at all, because we have individual sources simulated. So what was really worrying me and didn't make it into paper 6 is that I was trying to make some predictions for mid-infrared, but we know if we want to do a quick comparison with past instruments just to benchmark the model, we have to actually blend the objects to emulate the effect with Herschel or Spitzer. And that's actually a separate project that can be done with machine learning or with a student. But yeah, the objects are not blend, but we can blend it in post-processing so that things look more like what they are in the real universe or through a past telescope.
Okay, yeah, cool, thank you. So I think we move on, but please post questions on the Slack. So thank you very much. And we move on to the next talk by Vladan Markov on constraining the ISM properties of high-Z galaxies using carbon lines and statistical modeling. So if you could please set up your slides. Perfect, I can see it.
Okay.
You can see it, yes. Please go ahead.
Thank you. So I would like to thank the organizers for giving me the opportunity to present my work. And so hello everyone, I'm Vladan Markov and I'm a postdoc at the SNS in Pisa. And today I will present the main results of the project which I've been involved in together with my collaborators. So today I will talk about how we can constrain the interstellar medium properties of high-redshift galaxies using observations of carbon lines and a theoretical model. So we have heard in the introduction talk of this session why we want to observe high-redshift galaxies, why we want to study them, and the importance that they have on the reionization of the universe and metal enrichment, but also we want to study them in order to understand the formation of the first galaxies and their evolution. So my work here is mostly focused on the internal properties of these early galaxies, so on the interstellar medium properties. And the two main questions that we want to address in this work are: what are the ISM properties of these high-redshift galaxies and how do they compare with the ISM that we see in the local universe? And we want to also check if there is any correlation between these ISM properties that we derive and the C2 deficiency that we observe at high Z. So in order to address this question, we use first theoretical models that were developed by people in our group in Pisa. And also we use the data, so observations from the available data that we have. So we mainly used ALMA. So as we know, ALMA is one of the most important observational tools in the past decade, at least, for studying high-redshift galaxies and their interstellar medium. And so we specifically we use ALMA observations targeting the C2 line emissions, since it is a tracer of the mostly neutral phase of the ISM. And on top of that, we also use VLT data, so VLT observations targeting C3 line in these early galaxies. So C3 line is also one of the, apart from Lyman Alpha, of course, one of the most one of the brightest line in the rest frame UV. And it is mainly used as a tracer of the ionized phase of the ISM. So we use this combination of observations and models in order to constrain these ISM properties. So, but first I will speak a little bit about the C2 line. So this is a rest frame far infrared, one of the brightest lines in the far infrared at 158 microns. It is mainly used as a tracer of the dense and mostly neutral phase of the ISM, which is connected both with molecular clouds and the H2 regions, so the so-called photodissociation regions, or these PDRs. It can be also used for many other things, like constraining the global properties of high-redshift galaxies, and also we can use it to as a star formation rate tracer. So there is a very tight relation that was found between star formation rate and C2 emission. So it was found by Deleuze in the local universe. So they use a sample of these spatially resolved low metallicity dwarf galaxies, and they plot them here. This is a plot from Deleuze on this. So it's star formation rate as a C2 surface brightness, and we see that all the galaxies follow more or less this very tight relation. So, however, if we observe galaxies at high redshifts, we see that these galaxies do not necessarily follow this relation, and they show that they are all more or less below this relation that is plotted here in blue. And so this is a plot from Markov et al., which is in preparation, so to be submitted soon. So we show C2 surface brightness as a function of star formation rate surface brightness, and then color coded by C3 surface brightness. We show our sample of high redshift galaxies and some intermediate redshift galaxies as circles. And then also we include a subsample of spatially resolved high redshift galaxies from the Alpine survey. So this redshifts between 4 and 6. So as you can see, all these galaxies are lying below this Deleuze relation, and they show C2 deficiency. So there have been several theoretical works trying to address this problem of C2 deficiency in high redshift universe, and they found that, for instance, Ferrara et al., and they found that the main drivers of this C2 deficiency are overall different ISM properties of these high redshift galaxies compared to the local universe. So this is mostly, they're mostly driven by low metallicity, low density of the emitting gas, and these high values of this so-called burstiness parameter, Ks. So burstiness parameter is a dimensionless parameter that is used to quantify how much a galaxy deviates from the Koenig-Schmidt relation, which can be expressed in this way as in this equation here. So basically, if Ks is 1, means that the galaxy is a star-forming normal galaxy. If it's above 1, so it's 2, 3, or more, it is in a starburst phase. So so here we also plot 3 example models from Ferrara, so which pass through these 3 galaxies which are annotated and which are so these are the 3 galaxies that are detected both in C2 and C3, and we can see that the models can well explain the C2 deficiency. However, there is an obvious degeneracy between the ISM properties. So since we use only C2 and star formation rates, so only 2 observables. And this is an example again from Ferrara showing a high redshift galaxy which has C2 deficiency. So, and 3 different models from Ferrara can pass through the data point, and actually many different models can pass. And so these 3 example models show that if we have high Ks value, low density or low metallicity, we can explain the C3, so the C2 deficiency in this source. So in order to break down this, the degeneracy, and also to constrain the ISM parameters, since we have 3 unknown parameters, we need 3 observables. So besides the C2 and star formation rate, we need another emission line, which is used as the ISM tracer. In this case, in this work, we use C3 line, which is, as I said, mentioned. So so it is at 1909 angstrom. So one of the brightest terrestrial UV line apart from Lyman Alpha, of course, and it's tracing the ionized gas. So based on the model from Ferrara, Vallini developed a statistical model which uses these 3 observables, so C2, C3 line emission, and this the deviation parameter delta, so which can be defined as you can see in this plot, as a difference between the C2 surface brightness that we measure and the one that you would expect from the Deleuze relation. So in Vallini 2020, they use these 3 observables, which can be which depend on these ISM properties, which are in general unknown. So we can use so they use a Bayesian approach and the Markov chain Monte Carlo, and then they try to fit this observed data and so obtain the posterior distribution in parameter space for these unknown parameters. So we take the best fit values and one-in-one surfaces. So now that I have explained in briefly the models, so now we need the galaxy sample, so the data, and then we can do the work to constrain the ISM properties. So this is the full galaxy sample that we use, so that we gathered for the purpose of this work. So we select high redshift galaxies which have both observations in C2 and C3. We limit the sample to galaxies which have a detection in at least one of the 2 carbon lines, and for the other one we put an upper limit. So as you can see, most of the sources are actually have upper limits in C3. And so besides the 3 galaxies that are highlighted here, which have detections in both C3 and C2. So we draw a sample mainly from the literature and the archive, but we also have our own extruder observations targeting C3 line in a couple of high-redshift galaxies. So including HZ10. So for in this source, so I show the 2D near-infrared spectra of this source HZ10. We identify a C3 doublet line, which is blended in this case. And so on the bottom panels, I show 1D near-infrared spectrum, so with different spectral rebinings in order to just demonstrate that the line is there regardless of the rebinning. So we have a detection of C3, it's a new detection in a high-redshift source, and we computed the flux by well, fitting the emission by Gaussian. So now that we have
there's 5 minutes left.
Thank you. So now that we have the models and the data, we can finally constrain our interstellar medium properties. So as I have mentioned, we only have 3 observables. 3 galaxies which have detections both in C2 and C3. For these galaxies, we can constrain the ISM properties, and in this plot we show the so the burstiness parameter is a function of the density of the emitting gas, and then color-coded by metallicity. So in order to increase our sample of galaxies that we use in this work, and for this analysis, we also include a sample of 10 galaxies from Vallini 2021, which have also been, so their interstellar medium properties have been constrained in a similar way using an equivalent method to the one we use. But they only use C2 and O3 lines instead of C3 and C2 like we use. So the main conclusion from this part is that all of the high redshift sources that we take into account are very in a starburst phase. So they have a very high KS, so between 10 and 100. So this the data that we have are not very, I mean, statistically significant, but they imply that since all galaxies are starbursted, that the KS parameter, it's actually, that the Koenig symmetry relation is not a universal relation, and that it depends on so it evolves with redshift, and that at high redshift is probably shifted upwards. And then, so for the second question that we want to address, so if we see any correlation between the ISM properties that we derive and this delta parameter that we introduced in the beginning. So here we plotted the KS parameter as a function of this deviation delta parameter for this sample of galaxies that we take into account. So as you can see, there is this flat, there is some weak anti-correlation. It's not statistically significant, but so from there is some kind of trend. From this trend, you can see that this is in agreement with what we expect from the theory. So if a galaxy is in a more bursty phase, it will have more stronger radiation fields, which will ionize more of the ISM, which means that the PDR regions will be much smaller. And since C2 originates mostly from the PDRs, then C2 will be faint in these galaxies. So here we plotted the total density of the emitting gas as a function of delta, and as you can see, the correlation is much stronger here. So out of all the ISM properties, the N, so the density seems to show the highest, be the highest driver of this C2 deficiency. So it's also in agreement with theory. So if we have galaxies that are very diffuse with very extended C2 emission, they would consequently have a small, lower values of this C2 surface brightness. There are also some other effects here, including the CMB suppression effects for sources with low density. And so these are, I will leave you here, thank you, I will leave you here with my summary and conclusions, and stay tuned for the Markov et al. Paper.
Thank you very much. Is there a very quick question? If so, please just raise your hand or speak up. Maybe very briefly for me, I was wondering, so these ISM properties, they all assume to be spherically symmetric, or how can I imagine them?
So these same properties are sort of like the integrated properties. They are assumed to be the same in the entire galaxy, more or less. So yeah.
Okay, thank you.
Thank
So
you.
yeah, please post questions on Slack. If also something comes to your mind tomorrow or so, always fine. Okay, so we'll move on to the next speaker. We will have Nashwan Sapti talking about Galumi. So please. Yes, it's on. Thank you.
Hi everyone. Thank you all for tuning in. I'm very excited to tell you a little bit about Galumi, which is our first step in building a fast and versatile galaxy luminosity function pipeline to learn about cosmology and astrophysics with an emphasis on cosmology. So the UV galaxy luminosity function has already been widely used in studies of the physics of galaxy formation and the astrophysical processes involved. But it turns out that the same data actually also provides us with a unique and highly complementary handle to learn about some of the fundamental properties of dark matter. So in the next 15 minutes or so, I will give you a broad overview of what Galumi is about and how it can be used to learn about dark matter. But let me first start with motivating the why. So this figure here shows on the y-axis the scales that we can probe as a function of redshift. So K here is a wave number. So it's like one over distance. And if K is large, then it means that we're dealing with smaller scales. And if K is small, then it means that we're dealing with larger scales. Now, most of our understanding of the properties of our universe is based on observations of the cosmic background at a redshift of around 1000, and on a number of local universe probes, such as Milky Way satellites, cosmic shear surveys, galaxy surveys, and so on. The area enclosed by the black line here shows when and where non-linear corrections become relevant, and this makes the analysis of some of these probes much more complicated. But nevertheless, these data sets already tell us that there is dark matter in our universe, and that this dark matter is cold and collisionless at supergalactic scales. But that's it. We still have no clue what a dark matter actually is. And this naturally means that we need to come up with new ways to search for its possible properties. And one way in doing so could be to try to access scales and redshifts beyond those brought by these data sets here. It could be that some of the fundamental properties of the dark matter have a more pronounced effect in this regime. And that's exactly where the luminosity function comes into play. In essence, it provides us with a new handle on understanding the structure formation during an uncharted epoch. So the question now is, what can we learn from the luminosity function? So let's first look at how the luminosity function is constructed. So broadly speaking, the luminosity function has two separate components. The first one is the halo mass function, which is mainly affected by cosmology. And the second one is the relation between halo mass and the magnitude of galaxies residing inside the halo, which is also called the halo-galaxy connection. And this term here is driven by astrophysical processes. Now, from the cosmology side, we have a relatively good control over the uncertainties. And that's because the process of how dark matter halos collapse and form is reasonably well established, especially given the guidance that we have from embodied simulations. So for a given cosmological model, for a given dark matter model, we in principle know how the halo mass function looks like. And then the name of the game is to try to figure out which of these halo mass functions fit our universe the best. Now, one of the main challenges here is that some of the cosmological effects could be made by astrophysical effects, such as feedback processes. So ideally, one would like to separate these two contributions as much as possible. But this then also means that we need to come up with a way to relate the masses of dark matter halos, something we cannot see, to the magnitude of galaxies, something we can observe. So I'll now provide you with a very quick overview of the schemes that we have currently implemented. So in our base model, we start with the assumption that the luminosity of high redshift galaxies is dominated by young stars. And this means that we can relate the star formation rate to the UV luminosity using a conversion kappa tilde here. I think it's also called the Kennecoott relation. Next, we can assume a certain functional form between the star formation rate and the halo accretion rate. The F star tilde is usually chosen to be a double power law, simply because it seems to fit the data very well. The alpha star, beta star, epsilon star, MC are all three parameters that we will marginalize over in our analysis. And then finally, one can use an accretion model that is calibrated to embody simulations to relate the halo accretion rate to the halo mass. And in this way, we obtain a one-to-one correspondence between M halo and MUV. Besides this base model, we have also included two other models as shown in red and green. And in this way, we can test a number of astrophysical assumptions. So for example, in the red one here, we assume a double power law between the stellar mass and halo mass rather than the accretion rates. And in the green one, we can test this conversion factor kappa tilde between M star dot and MUV. And in this way, we can get a feeling how much our cosmological inferences depend on our astrophysical assumptions. Now, this scheme itself is not applicable at the level of individual halos and galaxies. That's because the properties of galaxies that we derive here only depend on the halo mass rather than the unique formation history of halos. So whatever quantity we derive here should really be thought of as an average quantity. And with an average quantity comes stochasticity. And the way we deal with stochasticity is to treat this magnitude here as an average magnitude. And then we assume that the magnitudes of galaxies inside halos follow a certain distribution with this average and with a width sigma MUV that we marginalize over in our analysis. So this way, we obtain the halo-galaxy connection. And from now on, I will focus on the blue model. So we can compute the luminosity function and obtain its dependence on our three parameters. So the first three panels here show how the cosmological parameters impacted the luminosity function. Those are the large-scale clustering amplitude sigma 8, the matter density parameter omega m, and the tilt of the primordial power spectrum. So if we increase each of these three, we basically increase the amount of halos and therefore the amount of galaxies. The next four panels show how the astrophysical parameters change the luminosity function. Alpha star, beta star change the slope of the faint and bright end respectively. Epsilon star controls the star formation efficiency, and MC tilts the luminosity function. Now, the main point of this figure is to highlight the degeneracies that exist between the cosmological and astrophysical parameters. So for example, if we plot the sigma 8 curves on top of the epsilon star curves, we find that at the level of the luminosity function, increasing sigma 8, so having more galaxies, could be mimicked by making the galaxies brighter. So you see that this degeneracy is not exact, but still quite strong. Now, this is a picture at a single redshift slice. And then as it turns out, this degeneracy direction is slightly different at different redshifts, such that when we combine data at different redshifts together, we can somewhat break this degeneracy and say something about cosmology. And we do that by using Galumi. So Galumi is a likelihood code that we have implemented in the publicly available MCMC sampler MontePython. And the reason why we have implemented it in MontePython is because in this way, it can be readily used in conjunction with other data sets, such as the Planck CMB likelihood or Pantheon JLA supernovae likelihoods. The current implementation contains a number of astro models that I've shown before, contains different halo mass functions, different dust calibrations, and so on. We have included data from the Hubble legacy fields, but also mock data from the illustrious TNG hydro simulations. And this mock data is especially important because it allows us to verify that our approach is actually able to extract the underlying cosmology. So it makes for a very important test. And finally, the code is available on this GitHub page. So now I will give an example of how Galumi can be used to learn about dark matter. So this figure here shows the matter power spectrum as a function of wave numbers, as a function of scales. The matter power spectrum tells us something about the clustering of matter. The colored data points are obtained from a number of different probes. So Planck CB data, weak lensing surveys, galaxy surveys, Lyman Alpha. And the black line is the 3D prediction for a cold dark matter cosmology. And you see that current data is in agreement with the cold dark matter paradigm. But as I've mentioned before, we still have no clue what a dark matter is. And one of the ways to try to understand what a dark matter is try to probe its small scale behavior. So the way we do that with Galumi is that we divide the power spectrum into 4 separate bins, and then we vary the amplitude of the power spectrum in each bin independently. So for the first bin, we use Planck CB data to constrain the amplitude. And in the other bins where Planck loses sensitivity, we have the luminosity function to cover this region. So we run a standard MCMC analysis. We compute the power spectrum at the center of each bin, and then we marginalize over all relevant cosmological and astrophysical parameters. And we obtain these 2 new data points. So we see that with current data, we are able to measure the matter power spectrum up to wave numbers of 10 inverse megaparsec, so scales of 0.1 megaparsec. And you also see that current data is perfectly consistent with the cold dark matter prediction. And this, of course, has consequences in alternative. Yes, it has consequences for alternative theories of dark matter. So, for example, if dark matter is warm, so it has a non-zero free streaming length below which it suppresses structure formation, you can see that with current data, we can already exclude such types of models. So to summarize, the UV galaxy luminosity function is a rich probe not only of the physics of galaxy formation, but also of the properties of dark matter. Galumi allows for a quick and versatile way to extract cosmological and astrophysical parameters. And we have a number of extensions coming soon, ranging from more data to a more flexible astrophysical model. So please stay tuned for that. With that being said, I thank you for your attention. Final thing I want to mention is that all of this is still pretty much work in progress. So any type of feedback, suggestions, criticism would actually be very much appreciated. Thank you.
Thank you very much. So are there questions? I didn't see a hand raised yet. If you have a spontaneous room, please just speak up. Slack is still great, but people sometimes need time for typing. So maybe in the meantime, I was wondering, you showed well, also cosmological constraints you can gain alongside, especially when, you nicely kind of bin it. What's implemented right now in Galumi as cosmological parameters that you can vary?
The cosmological parameters one can vary?
Yes.
So go back to this one here. So one can measure the large scale clustering amplitude, the matter density parameter, spectral tilt, and now also the amplitudes of the matter power spectrum. But we also have a model of small scale non-Gaussianities that one can also run to constrain deviations from Gaussianity.
And the warm matter mass that was constrained with the small scale amplitude of the power spectrum.
Exactly, because it suppresses the structure formation below its free streaming length. So it's small scales.
Okay, thank you. Interesting. There's another quick one. Please speak up. I don't see one right now. So please, again, post on Slack. And so thank you for the talk, and we'll move on to our next speaker, Lena Lenz, with automated methods to find the most distant quasars.
Yes, hello.
Hi. Okay, I can see the slides. Not full screen yet.
Can you see
Now.
them?
Yes.
Okay, perfect. Thank you. So yeah, hello everyone. I'm Lena. I'm a final year PhD student at Imperial College, and I'm working on automated methods to find high redshift quasars. Okay, so typically what you would do if you want to find high redshift quasars is you have your survey, you download all the images, then you can obtain database photometry, and then from those you can do color cuts. And then with those colors as its input, you can do, for example, Bayesian model comparison, and that gives you a probability that the source is a quasar. So you would also include some contaminant populations. And then you can rank those based on the probability and look at the most likely candidates, so visually inspect them. And then you can discard the ones that don't make any sense. And the ones that you think, oh, this looks like a quasar, you can do follow-up imaging on this. And then you can repeat these steps until you only have a few sources left. And on those, you can then do spectroscopy. And now, as we know, with upcoming surveys, there will be so much data. So this will be very inefficient, especially with the visual inspection. So what we want to do is to minimize the amount of visual inspection that is needed. So what we want to do is to swap this step with machine learning. And now we still have the Bayesian model comparison, but it will be used as one of the inputs for the machine learning classifier. And then we also have one other one, which I'll come to in a second as well. So overall, we have this data processing pipeline, where we download all the images, etc., etc. Then from this, we get the summarized features, and these we can then feed to a classifier. Now we have different kinds of classifiers. So I know some people don't like, machine learning, which is a fair enough point, So you can then instead use the features that we have and manually set thresholds for those. Just a point to the pipeline. So one thing that we do is that we fit point sources to the candidates. So this is useful for sources that might not be detected in one of the surveys. So then we still have some photometry information. Now, as a motor feature, I mentioned a feature is just an input to classifier. Is that, well, first of all, objects that are far away appear to be stationary. So we can move, model a quasar, which is a very high redshift, as non-moving between the passbands. Then also, because the quasars outshine their host galaxy, they have this star-like appearance. So we can fit them via a point spread function. And then lastly, they have a very, very distinct spectral energy distribution. So what we have is a template of 9 quasar SEDs. And then based on the observed photometry that we have, we can get a best fit SED and redshift. And this works in the redshift range of 5.5 to 12 in theory. So in total, we have this model of a stationary point source that follows the SED of a quasar. And then overall, the list of features that we have is, as I said, this chi-square that I just mentioned. We have this in each passband for each survey that we use. And then we can also get a maximum or minimum. We have the photometry of the database and our own calculated photometry, a quasar probability, and the estimated redshift. Just briefly to the data set. So we have optical and near-infrared data. And we're using a pre-labeled set from SDSS and Euclid from Daniel Mortlock and Stephen Warren. They basically used initially some color cuts, and then they visually inspected about 4,000 candidates. And so we are trying to reproduce those results. And now here, for example, you can see what we would call a good candidate. This is a confirmed quasar at redshift around 7. Here you can also actually see this distinct SED that they have. So you would have your Gunn-Peterson flow here, where you have no emission at all, and then here would be your Lyman Alpha emission line. If we use our best fit SED and subtract that, then as you can see, what we have left is only noise, which is great. So in this case, the chi-square, which would be very low, which is what we want. And here you can see a source that is moving. So this is definitely not a quasar, because we know quasar is stationary. And if you then look at the residual here, you can see the fit is very, very bad. So here we would get a very high chi-squared. And just as a side note, you might spot it here that we also reconstruct all the nearby sources. And this is useful so it doesn't get in the way of the chi-square calculation, which is on the pixel level, and also on the photometry calculation. Okay, so then as I mentioned, we have classifiers. We have 3 different ones with varying degrees of interpretability. So the first one, we manually choose our cuts and thresholds, and the other 2 are machine learning classifiers. So for the manual one, we only use basically two features, which are redshift and also server independent. And this means you can use them for any upcoming survey, basically, and you don't really have to change your thresholds for that. So the first one here is our quasar probability, where the contaminant populations that we have are MLT dwarfs and early type galaxies. And then here is our model of this stationary point source that follows the quasar SED. And those go quite well together because, for example, here you could have candidates that, based on color information alone, are likely to be a quasar, but actually they're moving or they're just not a point source, and then they will have a chi-squared. On the other hand, you could also have sources which have a good chi-squared, so they kind of look like a quasar, but they're much likely to be contaminants. So it goes quite well together. And in red, you can also see some confirmed quasars. So they all have a very low chi-squared and a high quasar probability, which is what we want. Then secondly, we have our decision tree. This is less important. It's mostly to, either find thresholds for a manual classifier, also to see if it makes sense what it's doing, because it's one of the more easily interpretable machine learning classifiers, and also to have a look at important features. But we do use another feature importance measure, which is much more accurate than this. And then finally, we have a random forest. This is just a collection of decision trees. So if you just had 3 trees here, and this would be your input, then the first tree would say it's a cat, the second one 2, the last one would say it's a dog, and then based on majority voting, you would get a cat, which is correct. And the difficulty with this one is obviously that you would have to retrain it for each new survey or each new data set you are using. But at the same time, it's much more efficient and just gives much more accurate results. Here are the results. So we're using the so-called ROC curve, which is the false positive rate versus the true positive rate. And the ROC curve is just this here. And then you have something called the area under the curve score, which is just the integral of this curve. So a perfect classifier would have a score of 1, and the random classifier would have a score of 0.5. And as we can see here, the random forest gives the best results. However, this decision tree is actually also quite good, given the fact that it's quite simple. Here is just the overall result as well. So if we use all of the features, the random forest gives the best result. So this is tenfold cross-validation. And then if we only use redshift independent features, so only our chi-squared and quasar probability, then again, the random forest gives the best result. However, our manual cuts classifier is also quite good at 0.73 of an AUX score. So this is quite promising, and yeah, we're looking forward to applying these methods on upcoming surveys such as Euclid and LSST. Yeah, thank you very much.
Thanks a lot for the interesting talk on the Quasar classifiers. There's applause. So, is there a raised hand? Oh yeah, I see one. Emil, please go ahead.
Hi, thank you for the talk. Very quickly, you said that the redshift that you are using is like redshift estimate. How exactly do you estimate the redshift?
Yes, so this is based on our Bayesian model comparison. So from this, if you have your quasar STDs, you can then obviously fit for those. So based on wherever you have your 9 templates and then also a set of redshifts, then you can see which combination fits best to your observed photometry.
Okay. Okay. And I just another question very quickly. So all of these, if I understand correctly, depends on the templates you are using, right?
Yes.
You can tweak your templates at like, are they okay, or you would like them to be better? I'm not from the field, so just to understand how close you are to what would be optimal in terms of templates for this exercise.
Yes, this is actually a good point. So the limitation is definitely are the templates, because obviously if it doesn't fit those, then both the chi-squared and the quasar probability will be off. So this is actually yeah, and would be an issue, but thankfully in our data set they all fit very well. But obviously you cannot model all of them, and this would actually be something interesting to include more templates to make it better. Yeah.
Okay, thank you.
Thank you.
Is there another question? Please raise your hand or speak up, and checking Slack. So far, I don't see another one. Again, as always, please continue to post also afterwards. And yeah, maybe I have a quick one. So you mentioned that the decision tree can be interpreted better than the random forest. So did you look into something there, the interpretability?
Yeah, so what we actually did, because the interesting thing with machine learning is to understand which features are more important than others. So in this case, the decision tree is more like just an initial test. But what is more accurate, what we used is it's so-called a conditional random forest. So you can then use conditional probabilities and then get your most important feature there. And yeah, as you can see here, all the chi-squared give the best values. I haven't explained the ones with the tilde. This is where I also fit for the source center. And this is quite useful when the sources move, because then the difference between the ones where I don't fit for it is very large. Yeah, and as you can see here, the chi-squared are basically the most important ones. And then you have the flux in Z, which is due to the redshift range we have in our training set.
Okay, so yeah, so with the conditional random forest, then you make it more interpretable than
yeah.
Okay, interesting. Thank you. Yeah.
Thank you.
So is there another quick one left for Lina? If not, I'd thank all the speakers of session 1 for today. And we will have a 15-minute break now. So yeah, please, I don't know, step out, get a coffee, whatever fits your current time zone best. And I'll see you again in 15 minutes at 15:15. And maybe for the speakers, it might be I forgot to mention this. So please, if you want to, you don't have to, on the Slack channel for the SIP, you can find a header at the top for the Google Drive, and feel free to put your slides there for reference. So, thank you very much, and see you.
Hi, can I just test my setting maybe?
Oh yeah, of course.
Right. I have made the dare of trying to put a video. So
so in that case, when you go to share screen, there's the two tick boxes in the bottom left-hand corner.
Mm-hmm.
So it should say optimize for video clip. Yeah. So just tick that, and then it eats up bandwidth, but it ensures that the frame rate somewhat gets through.
Okay, let's try that. So you should see my slides full screen.
Yep.
Okay, and now if I go there and I play this, you should see stuff moving. Is that okay? Amazing.
It's smooth for me. I don't know about others, but all good.
Okay.
For me as well. Yeah. So all good.
Great. Thank you so much.
Oh, I'm not sure if we have other speakers for the next session, but if you want to try also the setup, feel free.
So Emil is taking over now, just for the speakers for the next session. who are around that, yeah.
Hello.
Yep. Share this one. So you're seeing something moving, I guess?
Yes, I see your slides, yes.
And the next one, and yep.
Yes, yes, it works.
Okay, great.
Good.
That's it. Thank you.
Hi. Can
Hello.
I just test my screen sharing?
Yes, yes, please, go ahead.
Yeah, thank you. Do you see my slide?
Yeah, that works.
Oh, it's not working?
Yeah, yes, yes, I can see it. Okay.
Thank you.
Yeah.
Yeah.
Just a question, can you hear me well, or the sound is not good?
It's a little bit unclear.
It's very distorted.
Yeah.
Okay, so I'll try to do something about it.
Hello, can you hear me now?
Yeah.
Is that better?
It's much
better.
Much clearer, yeah.
Okay, thank you.
So it's 10 minutes. It's 10 minutes. You will give me a warning at 2:01.
Yes, yes. So you have 15 minutes. So you can use all the 15, and then we'll have no time for questions. But I will let you know when you have 5 minutes left.
All right. Okay. Thanks.
Okay. Great. So we have 1 minute to the time. I'm not sure if any of the other speakers who did not test yet wants to quickly test the sharing thing. Otherwise, we will start in a few seconds. Okay, people, welcome back. It's 15 past, so we are going to start. Just a reminder to all the speakers that, again, what I just said, that you have 15 minutes each, including questions. So ideally 12 plus 3, but I will let you know when you have 5 minutes left. And then it's up to you if you want to use the full 5 minutes for presentation or leave some time for questions, which would be super nice. So our first speaker is Roman Meyer. Roman, are you there?
Yes, I'm here. That's right.
Yes. So Roman is going to talk to us about learning from quasi-specters with variation autoencoders.
All right. Can you see the slides?
Yes, that's okay.
Okay. Great. Thank you. Thank you to the organizers for the opportunity to speak here. I'm very happy to share with you some of my very recent work on quasars and machine learning, two of my favorite topics. So the motivation for this work is really started from the IGM damping wing in high-redshift quasars. And I know Charlotte has talked about this a bit previously, but just as a reminder, here is a high-redshift quasar, 7.5 in black, and you have a red, you have a low-redshift SDSS composite spectrum. And you can see that most of the difference between these two happens around the Lyman Alpha line. You have, of course, no Lyman Alpha forest because of the Gunn-Peterson trough. We are in the Reionization era. But if you zoom in on the Lyman Alpha line, what you will see is that if you have some way of reconstructing the intrinsic emission, unabsorbed here in red, you will see that some absorption extends way beyond the Lyman Alpha wavelength, up to 1220, maybe even 1230 angstrom. And this is the so-called damping wing of the IGM because of the broad hydrogen cross-section. And this was predicted already 20 years ago in theory papers. And the nice thing is that if you can measure this absorption redwards of Lyman Alpha and the whole shape of it, you can put some constraint on the neutral fraction. And so there has been now 4 quasars, I think, for which we can measure this. And it's already putting very interesting constraints on the neutral fraction history of the universe. But with, of course, with Euclid and LSST, we will have way more quasars in the reionization era where we can do that kind of measurement. And so it's a really promising technique. Now, as promising as it is, this technique relies on having a good idea of what is the unabsorbed Lyman Alpha emission. And this is kind of tricky. I'll just highlight here a plot from 2 years ago where someone, David Raymond, made a compilation of different techniques looking at the same quasars and trying to infer the neutral fraction. And you can see there is a lot of scatter on the predicted value and also on the errors. And this is the almost surprising when you think that these are the same two quasars, but also these methods were all trained basically on the same training set as the SS quasars at low redshift, and they all report in their in these studies, they all report about the same residuals on the training set. And so when you think about it, you have a very good performance on the training set, but when you start to apply it at high redshift, it starts to diverge completely. And some of these methods are based on the same kind of recipes. And so it's kind of interesting that they all vary so much. And it suggests maybe that, there is an issue with robustness here. You do well on training set, but not on the testing set. And this is not just, this value that I'm showing here. If you look at the predicted Lyman Alpha line, they all look completely different. So this is not a subtle measurement. Some of them are completely different in their region, and that changed from quasar to quasars, meaning the outlier here might be another study on another quasar. So you don't know what's going on. And so I was looking at these papers for the past 3-4 years, and I had I don't know, a wild hunch. I thought, all of these methods, the one thing they have in common, most of them are based on PCA, some of them are based on neural networks, some of them are based on Gaussian mixture models. But the one thing they have in common is that they kind of fit or decompose or take as an input the wavelength redwards of Lyman Alpha. And then they find a way to correlate this to another decomposition of the Lyman Alpha line. And so I thought, you know what, let's get rid of this red to blue mapping. Let's do everything at once, and let's do it in the most non-linearly fashion, which is with the neural network. So we start with the training set that I don't have too much time to discuss here, but we can talk about this later. It's basically taking a DSS quasar, taking the continuum. I'm removing the Lyman Alpha line because I don't want, to depend on the Lyman Alpha for the prediction. And I also put some random masks because you all often have to mask emission lines when you look at high redshift quasars. I feed this into an autoencoder, which is basically a neural net, very simple. You take a high dimensional input, you map it down to a very, very low dimension. So here, 6 dimensions, and then you map it back to its original dimension. In fact, here it's a variation on the autoencoder. It's a denoising autoencoder because I'm providing a corrupted input, and I try to recover the real original truth. And it's not just an autoencoder, it's a variational autoencoder. So this is just a different architecture to make this a bit more Bayesian and to have a tractable posterior distribution of the latent space, the bottleneck layer, if you want. And we can try to impose a prior such that the values in this bottleneck layer are following some distribution. For simplicity, we'll just make it so that it's a Gaussian in 6 dimensions. And the info VAE, finally, comes from the part that there is a clever way to do this and make the training and the learning quite stable. And I refer you to all the papers I've listed here. But basically, we train this network to do 2 things. One, to make sure that its posterior distribution of the latent space is more or less Gaussian, follows more or less the prior. And 2, we have a mean square error for the full spectrum, which is we compute the error when it tries to reproduce the original spectrum. So this being said, as I said, the original motivation was the IGM damping wing. So we want to know how good we are on the Lyman Alpha reconstruction error. So here, maybe if you're in machine learning, you're used to the mean square error. This is not really what we want. Here we look at the residuals, the relative residuals. So we compare the predicted output x hat to the truth x. And if you take the mean of this quantity epsilon, this is the bias. And if you take the standard deviation, that becomes your uncertainty on your prediction. It's a statistical uncertainty for the whole training set or testing set. It's not really for one object. And this was the result. So that was let's say the benchmark, I would say. This is Davies et al. 2018. This is most widely used method on most of the papers. And you can see they have a bias of 1%, it's really nice. As I can say, you can always correct this. You divide by it, basically. And they have an uncertainty of about 6 to 12%. Of course, it rises at the location of the Lyman Alpha line and the nitrogen 5. Well, in our work, and I have to say, we did not specifically optimize for this. We optimized for the whole reconstruction with some other constraints. We get this uncertainty, which is about half what was in the visitor 2018. The bias is a bit higher, but as I said, we can correct this. So we've met the first, let's say, thing we wanted to do, which is improve on the Lyman Alpha reconstruction error. But as I said, this is a completely different approach because we're not just mapping red to blue. We are creating a latent space. We're creating a representation of all the quasars in its DSS. And this is what it looks like. So this is the posterior distribution of all the quasars that are embedded in the latent space. You can see it looks like a Gaussian. I mean, it's fairly well behaved, and we have done it properly. So now it follows a 6-dimensional Gaussian. Now I have sampled one single point here, and it produces a very nice quasar. I can also now move in this space, and you will see that smoothly I can create a whole bunch of quasars that have never existed. Right? I'm just moving in this space. I'm not taking the actual value of the DSS quasar, and I can create as many quasars as I want that have all different properties. So you can see here, blue, red, and quasar, maybe strong lines, small lines. Of course, Lyman Alpha is changing a lot. You might see, if you're a quasar expert, some helium-2 lines popping up just right now, and so on and so forth. I will even go further and say that each latent variable controls a very specific part of the spectrum. If you look now, I'm plotting a bunch of spectra, and for each bunch, I'm just varying one latent variable. So if you take the top one, for example, latent variable 6, I change this latent variable, and it only changes the power law of the quasar continuum. If you look now, let's say at latent variable 3, you will see that changing this variable will only change the carbon 4 line and a bit of the Lyman Alpha line. And this is how we can have a more robust and more, let's say, physically meaningful reconstruction of the Lyman Alpha line, because you can see some changes in the red part do not affect the blue part, and some do, and so we can trace this. We can even go further. The latent variables not only trace observational properties, they trace physical properties. I plot again here the latent space against the equivalent width of carbon 4. And you can see that there is a nice gradient for some latent variables, and for some there isn't, meaning that some of them are related to the carbon 4 equivalent width. Some others, it might be more interesting, we can also correlate this to the black hole mass. And let's be crazy. Let's just train a random forest to do a regression from the latent space to actual properties. So I've taken a spectrum, I've put it in the latent space, and now I can just infer a property. And this is what you get. So predicted versus true Eddington ratio of black hole mass and 4.5 max of the carbon 4. You can see for the Eddington ratio, it's not really well. So probably there is not much information encoded in the respirm UV of quasars. But for the black hole mass, we can do pretty well up to 20% error on the prediction. And so you could, in principle, apply this to the whole of its DSS, because this is trained just on the R7, which is a very small sample. We could do this for hundreds of thousands of quasars. So I'll leave you with my conclusions. We have started with a way to try and improve the Lyman Alpha reconstruction. We've ended up with a model that can create hundreds of thousands of crazy quasars based on a physically meaningful latent space. We can apply this to many things. I'll take questions. If you don't have questions, try to find the two fake quasars, and I'll post some answers afterwards. Thanks.
Thank you. Thank you for a very nice presentation. Do we have questions? Yes, Michel?
Hi, Romain. Can you hear me?
Hi.
Yeah.
Yes.
Yeah, sorry. Nice, very interesting talk. I wanted to ask you, when you try to disentangle the different parameter in the low dimensional space, are you basically providing a different prior, or how do you do that?
Right. So in that case, I think we're pretty lucky that we don't have to impose too much disentanglement on this. So some people use the KL divergence. Actually, it's not that useful in that case. So it emerges naturally. But you're right. We could have different priors, or we could have a GMM prior. But actually, with a simple Gaussian, it works quite nicely.
Okay. Okay. Yeah. Cool. Thank you. And to answer your question here, I think A and C are the fake one. Is it correct? No? Oh, maybe.
Maybe not.
Thank you. Thank you.
Okay. We have
I think
another
Andrea
question.
has another question.
Yeah, Andre?
Hi, thank you. Very nice talk. I had, I guess, two questions. The first one was about your comment about it being completely different. But if I'm understanding correctly, you're putting a mask on the Lyman Alpha when you're doing the autoencoding, no?
Yes. So I'm masking random wavelength, but I'm always masking the Lyman Alpha. The reason for that is I don't want, I mean, you could provide it, right? I don't want one latent variable to learn to produce all the Lyman Alpha line, right? I want it to.
Okay, but in principle, when this is used, you feed in like to do the reconstruction. I'm missing this part. Like to do the reconstruction, you feed in the spectra that is with the Lyman Alpha masked. So it needs to be able to predict the Lyman Alpha using the red side, just not a very direct fashion.
Yes, it never sees
not like PCA. Okay, so I think that's, for me at least, that's a little bit of a subtle distinction. But I guess my second question is, like, how do you get your uncertainty on the prediction? You quoted an error. Is this a uncorrelated pixel by pixel kind of RMS error? Do you have any more sophisticated way of including correlated errors? You know, construct covariance matrices, but that's just going one order.
Yeah. So as you say, this is the very first step. The one we find in all studies is just uncorrelated error. So that's really the whole error on the sample. It's just statistical. We could do correlations, of course, with, we could vary the properties of the quasars in the SDSS training set. But the next step, maybe it's a bit too heavy to train. You can predict the error as well. You can use Bayesian neurons on the output as well to try and predict the error. Yeah, that's future work. I think the correlated error is probably the easiest now. Yeah, try to do that. Thanks.
Okay, thank you. We have more questions, but I would ask people to ask on Slack because we are on top of the hour, so we do need to move on. Thanks a lot, Roman.
Thank you.
And our next speaker is Rodrigo Carvajal. Rodrigo, are you there?
I am muted also. Now it's okay. And let me share my screen.
Yeah, so Rodrigo is going to talk to us about high-redshift radio galaxies candidates prediction with ensemble machine learning.
Okay, thank you. Hello, everyone. I'm Rodrigo, a PhD student at the Institute of Astrophysics and Space Sciences at the University of Lisbon. And I'm very happy to talk to you about our results on machine learning and radio galaxies. So let's start with a very, very brief introduction on radio galaxies. So I'm going to define them very loosely as an AGN with some kind of radio emission that we can detect. So an AGN or a quasar that has radio emission, we can see it, we can measure it. We have some examples here in these figures. And why are we focus on studying these radio galaxies? It's because with radio emission, we can actually peer into the central engine of the AGN. We can see what's happening in the supermassive black hole with the accretion disk and everything. And also we can see the interaction of this AGN with the medium, as in the jets and some other structures. So the idea is that it's not highly dust obscured as another wavelengths. And also, since we don't have this interference from the other areas of the galaxy, we can use this information to peer into higher redshifts as well. So we can go very far away from us and try to understand their evolution, the evolution of these radio galaxies, and the overall structure and understanding of the epoch of reionization, if you can get there. So that's very nice. We have radio emission, radio observations, but it's not so simple because as they are high redshift objects, they are very, very hard to detect. So that's, we know about this, they can be very faint. Also, if we observe them, we want to obtain a redshift estimate. and that can be very expensive in terms of time and computational power. And from the point of view of the radio observations, in the latest times, it's been very hard to observe with any kind of radio observatory because of the actual observational properties of the observatories, of the telescopes. So it's very difficult to pinpoint the actual observation of the AGN and get their properties. But this is also coupled with a new problem, let's call it a problem in this sense, that with new observatories, new surveys, we have a lot of data, like gargantuan scales of data. And we have to actually now try to dive into this data, as we can see in the numbers we have in the table here for future and current surveys. And we have to actually try to balance the lack of radio observations in the past and the astonishing amount of data in the future. So with that, the traditional methods for detecting AGNs or quasars, or radio quasars in this case, is becoming very efficient because we have too much data. So what can we do to solve this? One way that it's been used extensively, it's using machine learning. And that's what we are doing here. So as our goals, let's say, we want to detect in some way using machine learning radio galaxy candidates from some observations or catalogs. And with these machine learning models or techniques that we are going to use, trying to understand the decision that these models are doing. So it's not only obtaining a result, let's say a catalog of radio galaxies, but also trying to see if there is any correlation or trend that the data that we are using is providing us. So how are we doing this? So we are using like typical machine learning models for this, like let's call it shallow deep machine learning instead of deep learning. So we are creating 3 consecutive models. I think it's a bit different from other approaches. So we are creating one model to detect from the data we are using if a source is an AGN or not. Then from the ones that we are predicting to be an AGN, we predict again if they are going to be radio detected or not. And from these radio AGNs predicted sources, we're trying to predict their redshift values. So it's like a pipeline of predictions. And also, for each of the models, we are using a technique which is part of ensemble modeling from machine learning. So it's called model stacking. So it's using several models all together, trying to predict the values, the things we want to understand, and then using these predictions, these outputs, as a new output for a meta learner. So that's stacking in this context. So let's go for our training data. We went for the head spring field. This is in the northern sky. It's a relatively large area, about 400 square degrees in the sky. And we are starting for all of our modeling, we're using photometric data. So we are going for archival data on catalogs, not images. And we're starting with detections in the CatWise catalog, that's near infrared. So we have about 7 million objects. That's everything. That's AGNs, that's quasars, galaxies, stars, anything else. And we are cross-matching that with the million quasar catalog. So it's a list of already confirmed AGNs or quasars, plus a redshift measurement from them. And also, for all of them, for 7 million, we are obtaining the counterparts in the infrared, in the visible, ultraviolet, and radio. And importantly, for the radio, we are not actually, let's say, measuring the emission, the flux, or anything. We are just assigning a flag, let's say, of if this source is being detected or not. That's for the purposes of the predictions that we are talking about. Then, yeah, so we have some numbers here that only 32,000 AGNs have been detected in this area, in this head spring field, according to the list we are using. And that's a very, very low fraction of them. So 0.5% of all of them, all of the 7 million sources. So we have also a problem of imbalance in the data, but we are trying to tackle it. And for the features that we are using is the magnitudes of the catalogs I told you about before. And also we are creating some another features, another properties, which are first the number of available bands. So it's like just an integer, a number that says in how many of the bands of the previous catalogs we can observe something. So it's 1, 2, 3, or up to 20 bands that we have access to. Then we are imputing the missing values with the limiting magnitude of each band. So it's saying we are assuming that if we don't have a measurement in these bands, it's because the source is too faint. So we are a sort of applying an upper limit for this. And then we also create some colors and magnitude ratios. And as I told you before, we are creating this flag for the detecting or not in the radio an AGN, and if it's an AGN or not. And we are applying these models in another area in the sky. This is the Stripe 82 field, so you know about it very well, I think. And it's the same idea. So we have a smaller area with the same, with the sources gathered from the same catalog, so cat-wise, and we're obtaining counterparts in these catalogs. So let's see how we do it. And we have here a confusion matrix for the AGN prediction. So you can see that the numbers are not so very good. So we have a F1 score of 0.6. That's pretty okay. And we can see, we can say, for instance, that one of the problems is the imbalance of the data. As I told you before, it's very unbalanced against the AGNs. And also, as I will show you later, I think it's a thing of not having too many extra models for the stacking because of the memory issues in our computers and servers. We couldn't use the same number of stacking models for this prediction. Then we take, okay, thank you. Then we take the sources that we think are AGNs and apply the radio model, and we obtain this confusion matrix that is almost perfect. So we are, for the AGNs, we think that we are doing pretty well. That's because it's not so unbalanced, the data, and also we have much more stacking models in the prediction. We take the sources that we think are radio, and we predict the redshift, and these are 400 of them that we can compare actually with previous values, and we have a dispersion and a deviation, an absolute deviation of 0.08 in redshift, on the normalized redshift, sorry, and an outlier fraction of around 18%. And that's again pretty okay, pretty good for these results. So good, we have our results. That's pretty fine. We can obtain a catalog of new sources, but we also want to understand what's going on with the models themselves. So we are using Shapley values. That's something like a feature importance, that we understand what feature, what property is driving the predictions, but for each individual prediction, for each individual source. So it tells us how much the inclusion of each of the features is driving the prediction from a median value of the predictions. So we have an example here for the AGN prediction, and that's so we have a subsample of sources from the full catalog, and we can see if we go from the bottom to the top, we start including new features. So how much of the inclusion is driving the prediction towards one side or the other? So we are starting with all of them being non-AGNs, and some of them at some point start to diverge towards being an AGN. And on the top, we have, of course, that the most influential ones are the outputs of previous models, and some colors here, and the number of bands that are measured. We have the same for the radio detection. So it's the same idea. We start from all of them being non-radio detected, and at some point we see the inclusion of some features is driving the prediction to one side of the other. And finally, the same for the redshift. So we start with a mean value of the prediction, 1.5, and the inclusion of the output of previous models is driving the final decision towards the final value. So what we want to do after this is go and observe the candidates that we have, trying to include new features. So uncertainties, morphology, something else maybe. And after this, trying to derive properties from the candidates, luminosities, black hole masses, you name it. And just to finish here, I want to tell you that mixing machine learning models works very well. So you can try stacking and sequential learning, trying one after the other to improve your results. And also the Shapley values can help you to understand what's going on inside the models and trying to think of new ways of analyzing the importance of the features, and that we have still plenty of room for improvement. So I will stop here and thank you for your attention.
Thank you. Thank you for the presentation. We have time for one quick question. I don't see anything on Slack, but please feel free to post questions there. And just a very quick question. What exactly you said meta learning? I didn't understand exactly what in the process are you calling meta learning?
Yeah. So maybe I'm using too big words for this, but it's only so here. So I take, let's say, 5 different models, random forest, XGBoost, whatever, and I predict the things that I want, and I take these outputs as new features for a new model, and that's my meta learning. Yeah.
Okay.
And that improves the results by a lot.
Okay, understand. Thank you very much. Thank you for the presentation. I don't see more questions, but please feel free to post on Slack, and then Rodrigo can answer that. Thank you very much.
Thank you.
So our next speaker is In-Tai Yang, who is going to talk to us about predicting Lyman Alpha emission from reionization era galaxies with supervised machine learning. So you have the floor.
Yeah, do you hear me? Can you see my screen?
Yes.
Yeah, thank you. Hello, everyone. My name is In-Tai Yang, a postdoctoral fellow at NASA Goddard. So today I will present my ongoing machine learning project on predicting Lyman Alpha emission from reionization era galaxies. So referring a great overview given by Charlotte Mason earlier today. So there are multiple means to trace the evolution of azimuth refraction. And I took a figure from the recent review paper of Robertson 2021, which display a compilation of observational constraints that shows quite a good agreement, but with a slight tension between their measurement at these redshifts. Particularly, my research focuses on the Lyman Alpha emission as a problem of reionization, as it's the strongest emission line and the preeminent emission from high-redshift star-forming galaxies. And the Lyman Alpha photons are easily scattered by neutral hydrogen in the galactic medium, so that could be utilized as a sensitive measure of azimuth refraction. So the Lyman Alpha transmission is in the IGM is a key quantity that reflects the ionization state of the intergalactic medium. For more detail, in theoretical perspectives, the IGM transmission to the Lyman Alpha depends on the Lyman Alpha velocity offset and the size of ionized bubbles, in addition to the reionization history that provide the evolution of IGM neutral refraction. And this also shows the line of sight dependency due to the inhomogeneous nature of reionization. So particularly, recent studies using reionization simulations find that the higher IGM transmission from UV brighter galaxies. And this mainly due to these galaxies are likely located in overdense regions where they create larger sized ionized bubbles. So in the same context, the various observational studies of Lyman Alpha emission have provided accumulating evidence for inhomogeneous reionization caused by the individual or groups of bright galaxies located in the overdense regions in the middle phase of reionization in these studies. So in my earlier study in Zhang et al. 2021, we provided our empirical measurements of the IGM transmission, which is defined as the relative ratio of observed to the expected equivalent width of Lyman alpha. So we find that the IGM transmission appears to be higher for the UV bright galaxies with greater than 90% confidence. So the cartoon on the right is summarizing the inhomogeneous process of reionization at redshift above 6, which is consistent with the data and the interpretation in our study, as well as the predicted what is predicted in the theoretical studies. So summarizing the cartoon figure, the galaxies with higher UV luminosity have larger ionized bubbles around them, and this allows the higher Lyman alpha transmission in the IGM. So all of these findings are suggesting that the true nature of inhomogeneous evolution of reionization. However, the observational constraint on the Lyman alpha transmission is still critically limited in terms of the number of targets in deep spectroscopic observations and the field of view coverage, which must be larger than the typical scales of ionized bubbles. So we have a good amount of predictions of the reionization models, but still lack of observational data to constrain them to reduce the systematics. So the future observations with JWST and Roman Space Telescope will push this limit soon. However, the observational constraints depends on the assumptions on the intrinsic Lyman alpha emission during this epoch, which I am trying to predict in this study. So how can we predict intrinsic Lyman alpha before being attenuated by the neutral IGM? So one earlier study with the machine learning approach, Lundholm et al. 2020, shows successful results on their Lyman alpha prediction. So this study utilized 42 galaxies at lower redshifts from LARS and ELARS projects with 21 variables measured from HST coarse spectroscopic data as well as the broadband photometric data. And by applying the multivariate regression to the dataset, they provided successful predictions on the Lyman alpha luminosity of these galaxy samples. And so this approach have huge potentials in reionization studies. For instance, predicting the Lyman alpha luminosity function and the Lyman alpha intensity mapping and the applications to reionization studies. So what am I doing for doing this? So as mentioned, I'm focusing on the placing the observational constraints on the Lyman alpha transmission in the IGM, which needs the assumptions in the intrinsic Lyman alpha equivalent width. So here I'm implementing the machine learning algorithms to improve the use of Lyman alpha as a probable reionization based on the Lyman alpha predictions for the reionization era galaxies. The goal of these studies are the first, the understanding the Lyman alpha systematics at higher redshifts of redshift greater than 3 with the machine learning algorithms to minimize potential redshift evolution of these Lyman alpha emitter equivalent width into the epoch of reionization. And the second, predicting and analyzing the Lyman alpha emission from the redshift 6 galaxies. And ultimately, we will investigate the evolution of IGN diffraction during the epoch of reionization based on this machine learning inference. So in order to do that, we utilize one of the great public data set of Murchison survey in this parallel study. And we derive the galaxy physical properties from acid fitting using HST photometric data. One notable difference from the Roonholm et al. 2020, we only utilize these minimal physical variables based on photometric data. So although the spectroscopic information is truly valuable, but it still costs a lot, so particularly for the deep high-resolution spectroscopy observations. So I'd like to test if we can provide a decent level of predictions without the spectral evolution information of the galaxies. So this is the critical in particular for reionization era galaxies, as we have the current access on the photometric data set for a larger population, but they're relatively limited in the spectroscopic data. And in training a machine learning system, we test multiple popular supervised machine learning algorithms and define the random forest regressor as the best performer. And we finished the optimization and to achieve the maximum performance. One thing that I want to point out about the data set, so the significant portion of the Murchison Lyman Alpha emitters do not have their HST counterparts in the existing HST catalog. So we separately perform the source extractor runs based on the REST UV combined detection imaging. And we recover the 70% of those Lyman Alpha emitters without HST counterparts and incorporate them in our analysis. So in total, we have over 400 Lyman Alpha emitters available for training machine learning system.
5 minutes.
Yeah, so this is an overview of our project using the supervised machine learning. I will go over quickly how our machine learning system is trained and tested and make predictions. But the first, we derive the physical quantities from the acid fitting with HST photometry and measure the Lyman Alpha equivalent width from spectroscopic observation. And from this data set, we create input variables listed here. And the target variables in our system is the Lyman Alpha equivalent width. And through the general steps of a model evaluation, selection, fine-tuning, and we developed an inference for Lyman Alpha equivalent width with this trained machine learning system. And our goal is to make the predictions of Lyman Alpha equivalent width for the reionization era galaxies. So we feed the same input variables of the reionization era galaxies to make predictions. For testing these predictions, we compare our predictions to the existing deep Lyman Alpha observations published in Zhang et al. 2020. As described earlier, so we made the predictions of Lyman Alpha emitter first by applying the random forest regressor to the Murchison training set. So this is the testing of our inference model. So this plot shows the predicted value in y-axis compared to what is observed. And we see the quite nice predictions with R-square value around 0.8. And while one might concern about the use of machine learning as a black box, but the feature importance analysis in random forest regressor provide us how important each feature is to predict the target variable. So I'm showing the feature importance scores in this table, and you can see the star formation rate is on top, and the dust extinction and stellar masses come next. And this result is more consistent with what is suggested in what is found in the Roonholm 2020. And lastly, based on the trained machine learning system, we predict Lyman Alpha equivalent width of the 10 Lyman Alpha emitters detected at redshift of 7. And you can see here the predicted values mostly agree with the observed within the uncertainties. And the over predictions could be generally expected due to the strong origin attenuation at these higher redshifts compared to the low redshift image dataset. However, the one interesting point is that we see the significant under predictions for this one, the pink point. This is maybe due to some unexplainable feature from the MUGE data, MUGE galaxies. For instance, possible IGM contribution or extreme metaphor stellar population. So this is the current summary. So I will stop here delivering my summary and take questions.
Thank you. Thank you for the presentation. We have time for one quick question. Don't be shy. If you can type your question or raise your hand if you have it. There is a question. Yulsan, do you want to pose it yourself?
Let me try. Yeah, sorry about my video. Thanks, Inte. I'm just followed your talk. Maybe I missed the earlier part of your talk, but I'm just curious, how do you estimate the error of a prediction?
Oh, so I created the simulated data set based on the Monte Carlo simulation and make the predictions multiple times, like the 100 times, and measure the uncertainties.
So you basically drop the few parameters and the recreated sample. Is that how the random forest, the machine learning works?
Oh no, the random forest one is worked on the given data set, and in each measurement, I created a new Monte Carlo simulation to make the individual predictions. So I reiterate this.
Okay.
Making prediction status for likely 100 times.
Thank you.
Okay, we have one more question on Zoom, but I would ask you please. I would ask Intai please to answer on the Zoom because we are on top of the hour. We do have to move on. So please take a look at the question on Zoom and answer that. And so thank you very much for the presentation. And we can go now. Hello?
Oh, no. Yeah, thank you.
Thank you. Good. So we can go now to our next speaker, Chris Barrow. Chris, are you there?
Yeah, 1 second.
Good. So Chris is going to talk to us about decoding Lyman Alpha spectra and halos. And so you have the floor.
Yeah, thank you very much. And also warm thank you to the other organizers. My name is Chris Barwell. I'm a postdoc at the Institute for Theoretical Astrophysics in Heidelberg. And I want to talk about decoding Lyman Alpha emitter spectra and Lyman Alpha halos. I'm mostly working on the computational side of this. But first, let me start with just bringing up some other surveys.
Chris, just a moment. Can you minimize the gallery with, because it's on the top of your slide, the Zoom gallery with the names of the participants are on the top.
Yeah, okay. We got it?
Yes, that's better.
Awesome, sorry about that. All right, so before coming from coming back to the computations, so there are quite a few observational data sets coming up in addition to all the surveys that have been mentioned in the conference abstract for Lyman Alpha. I just want to mention HETEX on the Hubble UltraD telescope. So you really have in the order of 1 million Lyman Alpha emitters that are to be detected in a blind integral field spectroscopic survey. So you really raster the sky on 400 square degrees. And that also means that you have like a huge amount of data, like 10 to the 11 voxels. Similarly, you can look at the prime focus spectrograph on Subaru that will follow up on 10,000s of Lyman Alpha emitters. And of course, you can pick many of the other instruments on various telescopes. So, right, point is there's lots of Lyman Alpha data coming in and already available. And similarly, we want to have something on the computational side because there's a big complication being that, okay, so you have some Lyman Alpha signature, let's call it that way. So you have like Lyman Alpha emitter spectrum, you have a Lyman Alpha halo and like a 1D, 2D view, maybe even a 3D view. You can try to extract all kinds of physical information. It could be let's just take the example of like wanting to know more about the gas structure and kinematics. And then there's the complication in there being that you have the Lyman Alpha radiative transfer in there, as already pointed out, right? So you have a photon that is, let's say, originating in a galaxy. It's being scattered up to 1 million times. And at that point, once it reaches the observer, you do not really know the spatial origin nor the actual initial spectral information it was carrying, and that complicates things, right? Because it's not straightforward to map it back to the actual gas structure anymore, which is what you want to extract, right? And this is where simulations come in because I know both, right? I know the actual gas structure in these simulations that I then forward model the Lyman Alpha onto. All right, so what I mostly do is I use galaxy formation simulation. I will choose one. On the next slide, then you put that into a Lyman Alpha radiative transfer code, right? So that propagates the photons, and then you reduce the data to whatever observable you want. Right? So that gives you some simulated Lyman Alpha data, right? So what I've been looking at now is rather, let's call it the simpler ones. So you look at Lyman Alpha emitter spectra and the IgM imprint. We have already heard about this by Charlotte. Where you do this in the Epoch of Reionization, but even once you go post-reionization, there's quite a bit of imprint. Similarly, you can look at Lyman Alpha halos, and you can also think bigger, at least spatially. You can go to intensity mapping, trying to detect the cosmic web. You can look at Lyman Alpha forest, right, from crazes and cross-correlate and all kind of stuff. Right, and then the question really is like find suitable statistics that help you to really go back from the Lyman Alpha data that get an observations to some kind of physical insight. Okay, so getting more specific, what I've done is I usually pick TNG simulations, right? It's just like a hydrodynamic simulation with lots of baryon physics and a quite competitive regime between having a statistical sample of galaxies and high resolution. So then we plug this into Lyman Alpha radiative transfer code. So I'm using the one that was originally written by Christopher Behrens and that I've been maintaining since. So take a snapshot, post-process it. And what's important here is that you can nearly use an arbitrary simulation, really. So we've implemented all the different gas geometries you could think of. Depending on your interest, also moving to the Epoch of Reionization, right? You can plug in another RHD simulation, right? And then you do the data reduction step. This is actually kind of interesting, right? Because right now there's no machine learning. So the machine in that sense is me, right? So you interactively want to explore these data sets based on like what kind of photons, like where they originate, which origins, right? Like are important to something. And for that, you want to have it interactively, right? And then you think how to scale that up on a cluster and having it available on various GPUs and like trying to interactively work with that. Then you reduce the data to whatever you come up is a suitable statistic, and you can actually do some science. Right, so I want to mention two of these examples where I'm using this kind of data for rather simple statistics, no machine learning. This is what we want to do in the next step then. As we already heard, right, you have a Lyman Alpha spectrum that's usually double peaked. It's also often asymmetric. And even post-reionization, you have to ask yourself, like, what is driving the redshift evolution in this peakiness? It's not that easy. You could think of, right, like depending on the feedback mechanisms that you have, some velocity structure that gives you an asymmetry, or you could also think about the intergalactic medium, right, still having an imprint. And so we use this framework where we just calculate transmission curves for different different lines of sights for all the halos in a given mass range. And then on the small scales, right, that we do not properly resolve, you can also apply some kind of toy model for the spectrum, right? And then you try to basically combine these toy spectra with the transmission curves that give you a mock Lyman Alpha emitter spectra, right? And now you're thinking about, okay, how can I statistically break, for example, this degeneracy that I mentioned of small scales and large scales, right? And an easy way that we just came up with just as a proof of concept, right, is that you look at the peak count. Why? Because the peak count is somewhat the amount of peaks that you have in a Lyman Alpha spectra, right? Usually it's single peak, double peak. You can also think of triple peak, right? And it's very hard with radiative transfer small scales to get a triple peak emitter. However, it's very easy to have a trough for the attenuation of in the IGM sitting there, basically splitting up your peaks and giving you 3 peaks, right? So this is how we can differentiate the scenarios, right? And like where it's useful to find, looking at new kind of statistics that we can then go back to observations and trying also to look at this, right? So this is just a proof of concept. So we made these transmission curves available on Zenodo in parts, and yeah, like so even for this kind of simple data where you just have 1D data, yeah, there's certainly better statistics that we try to find to improve on this. Right? So another application will be simulating these Lyman Alpha halos, so this extended Lyman Alpha emission around star-forming galaxies, extending up to a couple tens of kiloparsecs. I'm showing some observations on the left here. That also maybe demonstrate the technological advance that we had. Right, and before you really like pinpoint the physics of the gas, right? Like you should start out asking like, what is the source, like origin of these Lyman Alpha halos, right? Is it scattered Lyman Alpha from the galaxy itself that like basically scatters into the surrounding? Is it diffuse emission in the circumgalactic medium around the galaxy itself? Is it unresolved satellite galaxies shining into? You can like ask all these things, right? And within this framework, we can model this, given these modeling assumptions that are in there, right? We model different emission mechanisms, and then we actually reduce it again, also just back to 1D, just because that's what has been, for good reasons, been done mostly in the past when you looked at observations of these Lyman Alpha halos. Okay? So what we can do then is, because we can tag in the simulations, we can tag all that information about the Lyman Alpha halos in there, right? Like where did the photon originate, where did it scatter, at which time, blah, 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 blah. So
5 minutes.
Thank you. So here you see a prediction of the Lyman Alpha halo radial profile stacked. So this is what we would get as a prediction, and then we can split it into different origins. Origin meaning where photon really originated from, and then like was scattered into these outskirts up to like 50 kiloparsecs, right? So what we saw here is that actually it's mostly scattered Lyman Alpha emission that we see, right? So that was from the ISM scattering outwards and dominates this radial profiles. Something like, again, like that we figured out, right, just by exploring this data cell that I think is not really clear, is that we see a flattening in the radial profile. And in our case, right, under our model assumptions, what we find is that this is due to Lyman Alpha photons that scatter from other halos into the targeted halos circumgalactic medium, and then scattering towards the observer, right? That gives rise to a flattening. Right? And there are also other components that weren't that important for us. But yeah, so point is, right, you can, by exploring this data, by coming up, like just interactively exploring, trying new statistical measures, you could like find out new things to look for. So also just briefly mentioning, right, so there's also lots that can go wrong, like really comparing this to observations, but just naively speaking, sanity check pass, so like results look good when compared to observations. Okay, so just let me put this into context and summary and outlook, right? So we have these large Lyman Alpha data sets from simulations available, right? So and that's for two purposes, right? First, to explore the relevant physics that's shaping these Lyman Alpha signatures, and then in the second step, to compare to and interpret observational data sets, right? Both in the simulations, we have massive data sets, like we can like have 10,000s and 100,000s of these Lyman Alpha halos and extended objects. And then also on the observational side, like we're matched equally in the near future, right? Like, so we've done primarily very simple statistics until now, right? Like just because we were looking in 1D, right? But then the idea is, and that's what's really so exciting about this integral field spectroscopy, like when you try to look at the Lyman Alpha cosmic web and like really the circumgalactic medium, right? There's really progress in the observations, and similarly, we aim to do the same, and that's what we need the statistical measures for, maybe even something buzzy like machine learning to pick up features that basically help us map back these Lyman Alpha signatures to the physical properties. That's it. Thank you.
Thank you very much. Thank you for the presentation. Do we have comments or questions for Chris? Andre?
Hi, thanks. Nice talk. Perhaps I missed this connection earlier, but you mentioned constructing these large databases of simulated spectra, which depend on the porosity and structure of the ISM. How are you, what's the plan of constraining these models with data in some way? Do you have, how are you confronting them to data? And then what specifically do you expect to learn for that from that? Like, is it just, you know, differentiating between 3 classes, or what do you expect to gain out of that?
Right. So yeah, that's what I mentioned, right? Like what the only thing I've really done is using these toy models, and what I've seen is that you already went beyond this, right? By on the small scales imposing some kind of I guess shell model whatsoever, where you put in like an outflow velocity and column density and so on. So this is not what I've done, right? So this is really simplistically just these 3 toy models, and see whether you can differentiate it then, right? Like once you introduce like a physical spread in all these properties, right? It gets way more complicated. So I haven't followed up on this yet. I know that other people also Sid Goering is working on this, right? Like using these kind of transmission curves that I've presented, and then on small scales using a bunch of shell models interpolated with a on an interpolated grid. Mm-hmm.
Okay, thank you. There is one more question by Caroline that I will ask you to answer on Slack, please, because we are on time, so we have to move, but please answer, and other people feel free to also pose more questions there.
Thank you.
Thank you. So our next speaker is Bene Haweda. Bene, are you there?
Yep, I'm here.
Yeah, good. So Ben is going to talk to us about probabilistic selection of high redshift candidate galaxies from imaging. So you have the floor.
Hi, thank you everyone for listening, and thank you for letting me talk about this. Thank you to the organizers for this awesome conference. So my question is, can machine learning help us identify high redshift candidate galaxies? I'm an associate professor at the University of Louisville, and so I'll go straight into the motivation, which is too much data, so little time. Knowing that Euclid and Roman are, well, especially Euclid is right around the corner, and it will start pulling down lots of near infrared imaging. And thanks to the 20-year lifespan that we now expect, James Webb and Euclid will form a team to explore the high redshift universe. So Euclid will be the target selection for James Webb spectroscopic observations, for example. So it would be really useful to have an unbiased probability that the source is in fact a high redshift, meaning higher than redshift 6 galaxy. So can machine learning do this? Is this a good enough, or is this an interesting problem for machine learning? And so you can use catalogs. So we know how to produce catalogs. We're pretty confident what goes in catalogs of objects, and we have those. Can those be used, or do we use images as input? No, traditionally we select high redshift galaxies from the Lyman dropout. So as you move your spectrum over to higher redshift, you drop out of all the optical bands, so you don't see them in the visual filters. You do see them in the reddest bands of HST. So you're just using colors really to select a galaxy, and on top of that, you would cast a critical eye on the near infrared image and see if that strokes with your idea of a high redshift source, if it's not too big or anything like that. Then you would go back and use the Spitzer Space Telescope and actually confirm it using the flux that you would see at the 3.6 and 4.5. So you use the J and the H band near infrared image from Hubble for an accurate position, and you would deconvolve then the Spitzer image in order to get a flux. And so you would get rid of things like lower redshift dwarf galaxies, or for example, MLT and Y dwarf stars in our own Milky Way, and you would get an accurate photometric redshift, and so that's sort of confirmed would confirm the high redshift status of this object. So we don't have Spitzer anymore. We do have James Webb, but that's a lot more expensive to do, and Spitzer would take a much larger field of view. So there's a cost benefit there in order to start confirming all the sky high redshift sources in the sky that way. And so I got to thinking, what are the other parts of the morphological space that I can use? And so I looked at the Morishita paper from 2018 from using HST, and I noticed that a lot of the visual rejections were essentially based on size. Not all of them, but a lot of them. And so can you use size as a prior? You don't want to completely use size as an input parameter, because the sizes of galaxies is an actual interesting thing that you want to study, but you can use it as a sort of soft cutoff. And so, but that depends on the kind of size luminosity relation that you're assuming, and the luminosity function that you're assuming. But essentially, you can put in a cutoff, and you're getting rid of maybe the brightest object in your sample. Depending again on what kind of size luminosity relation you're using. So anywhere between 7 over redshift 6, you might lose a few objects that way, but it would be a good way to keep culling and automate the culling of high redshift sources. Another thing that I was exploring, sort of in the similar vein, is the morphometrics. So putting a number on what a galaxy looks like. Usually we use that for much lower redshift objects, but with Hubble or Euclid or Roman in the near infrared, these galaxies are marginally resolved, and so there is a little bit of morphological information, not a lot, but there is a little bit in there. And so I had a student look at that, and the redshift 8 galaxies do seem to cluster in morphometric space between Gini and asymmetry. They're a little separate from actual point sources, and they're clumped together. So that's another promising hint that we might actually be onto something here to expand our catalog, our feature space. I'll get to that in a minute. So what's the data that I want to work on next? That's the Superborg. That's a compilation of all the Hubble pure parallel observations. It's all homogenized. It's a fantastic catalog. So it has an optical filter. There's usually a choice of 1, maybe 2. And then it has typically the J, H, and 1 of the Y filters to go with it. It's all well described in Morishita's paper in 2020. And so this is a nice public data set. And the best part is there are 316 fields. So it's actually a really large, shallow survey that's as homogeneous as it's going to get. And wherever there was Spitzer data to go with, there is actual Spitzer fluxes available as well. So this seems like a good large catalog to start doing something that looks like what we're expecting from Euclid and the Roman Space Telescope, but start doing it on actual data. And the second part is that we have labels from the Morishita paper. So we have a feature space, that's the actual catalog, and we have the labels from the Morishita paper as well. It's either a high redshift source or it isn't. And so are there any algorithms that can identify the high redshift targets from everything else just using this feature space? So that was my first, I'm just getting started on this, so this was my first tryout. The problem is that it is still a very imbalanced data set. There are some 60,000 objects that are labeled not a high redshift source, and not a high redshift source is also not a very clear label. It's a negative label, right? So it's just saying it's not that, but that leaves you with a wide variety of sources that have different properties. So maybe that's not the best labeling. So we try I started and try a few feature spaces and machine learning algorithms. So first question to ask yourself is, what kind of problem is this? Is this actually classification, high redshift, yes, no? Or should I use regression? Is basically, should I take my catalog and predict a photometric redshift or redshift interval? So which part of the catalogs are useful? Which part of that feature space is actually something that I should use? Are there bits that are redundant? Is it homogeneous enough? And is there enough resolving power? Do I have enough bits of information to actually turn the whole thing into a reasonable classification? This is a high redshift source. Yes, no. So try some simple ones like a decision tree and a self-organizing map. Decision trees are supervised learning. Self-organizing map is unsupervised learning. Why pick these two? Because I know about them and I'm still learning machine learning. So those are the ones that you sort of get started on. The decision tree, of course, I left it completely unconstrained. So it started splitting up this parameter space over and over and over and over again until it finally had separated out everything into different redshift bins. This is unworkable. And in fact, if you then use a training set on it, the training set's fine, but if you then use a validation set on this, this is not very useful. But the matrix here sort of tells you the story, which is that you have many labels. So it gets really fine in redshift 6, 8, 8.5, 9, 10. Like that's something that we were interested in because that's where the epoch of reionization is happening. So we want to know exactly where the photon Z is. And then there's that other label of everything below redshift 6, which is, the rest of the universe. So it's unbalanced. Yes, if I let this keep cutting and separating out, it will actually get everything where it needs to go, but that's an impractical approach. If I then go like, well, let's balance the data set, let's reproduce the high redshift sources until I have just as many in each category as the redshift less than 6 category, then you really see what the problem starts to appear. You have high fractions of crosstalk where you are starting to misclassify things. And it's not just, oh, it's a redshift 8.5 and now it becomes a redshift 8. That's something I'm quite willing to live with. It is more, it's a redshift 8.5 and now it's misclassified as a low redshift source. So this is something that we need to look at further. Oh, great. So the decision trees, what do those trees tell us? The labels are unbalanced. The classification of just saying like, oh, it's 100% not high redshift would still be 98% accurate. So we need to do better. Rebalancing shows the poor performance, and the trees are unworkable or not accurate enough. So, but it does show us that the feature space can or probably can discriminate this. It might just need 1 or 2 extra features. We need to feature engineer that a little bit. All right, self-organizing maps. Instead of doing something with labels, you first let the algorithm, the self-organizing map, sort of group similar looking objects together. And this is sort of where I was hoping that perhaps this would identify hitherto unidentified high redshift source group, for example. So you group everything by similarity and sort of learn every field, every node learns from every new data point. And so where do the high redshift sources end up? Well, here's the weight map. As you can see, we're sort of using every aspect in the catalog to a different degree, meaning that things like size, like flux radius, class star, and these morphological features that were in the catalog already are used a lot differently than, say, the colors, the fluxes below that. This is where the high redshift sources end up, and so they do not end up in a neat clump saying like, well, here's the redshift 10 candidates, here's your redshift 6 candidate, redshift 8 and redshift 8.5 candidates. Like they're not neatly clumped together where I could say, oh, those nodes correspond to high redshift sources and everything else doesn't. It doesn't separate out that well yet. Okay, lesson learned. But it does show that they clump together somewhat. So it really shows that we need just a little bit, not a terrible amount, but we need a little extra information in order to start, extra features in order to start separating high redshift sources from everything else out. The motivation, once again, is Euclid and Roman. The moment that we start having these imaging surveys, we'll have lots of similar near-infrared filters of similar width. And it would be interesting to see if we can actually identify them. So we need the morphological component, I think, as well. So this is just to show that we won't get information beyond 2 microns. So it is neat to use the IRAC fluxes when they're there, but can I actually, so I'll have to cut the feature space and like remove the Spitzer features and add morphological features and maybe size, and as a combination, see if I can identify reliably if something is a redshift below 6 or above 6 object. So conclusions, there's definitely something machine learning can try. This is it feels like we're pretty close with this. If it wasn't clear, I'm just getting started with this project. So we can identify high redshift candidates in near infrared imaging, and that's critical for both Euclid and Roman to have a good high redshift yield. We won't have that 2 micron information unless James Webb observes it. And so if you want to get the candidate for James Webb to go start observing these things, then you maximize the feature space. So use size and morphometrics in order to get the maximum piece of information that you can use in order to say this is a highly likely greater than redshift 6 source. It's encouraging, but we're not quite there yet. I think I'll move to 2 labels, just saying if it's a high redshift source or not. So just call it redshift 6. And also try a couple of regression algorithms. So basically predict the value of the redshift rather than saying it's in this particular bin, using redshift as a label rather than, so you're using the redshift as a prediction rather than a label. And so those are the 2 things, and I'm going to try a bunch of new algorithms that I've been talking to people. What would be a good way to do this on a fairly imbalanced data set? Remember that the data is optimized to identify high redshift sources, but the majority of sources in the data isn't a high redshift source, so I have a very unbalanced data set. So that'll be a very interesting challenge to go see if we can do as well as photometric cuts, visual inspection, and then probability photo Z. That's what's been done before, and sort of holistically approach it straight from the catalogs all the way to identify the high redshift sources. So I'm happy to take questions at this point.
Thank you. So do we have comments or questions from any? We have time for one quick question. Caroline?
I have a really quick one, and I'm sure I missed this, but so where did you put the cut between, like, to label high set?
Put it at redshift 6. So what I did, so I'd rather naively just started with, you can see it here, I had 6 labels where these are sort of the categories that come with the catalog, so to speak. So these are below redshift 6 galaxies, these are redshift 6 galaxies, these are redshift 8 galaxies. There were these, that label was there, so it was the easiest thing to use. So I got started on that. But what I think we'll end up doing is basically say everything that's redshift 6 or less than redshift 6, that's one label, and everything that's not that is the high redshift label, for example. So simplify the labeling a bit. And perhaps get rid of the label altogether and just say, can I give a redshift estimate based on the whole catalog? So rather than cutting in like do hard cuts in color space, and then do a visual inspection and then do a photo Z, just go straight to this is the redshift that both the shape and the size and the colors imply.
Okay, so below 6, there was no other subclasses.
There's no other subclasses, partly because you can't do photo Zs below 6 if you mostly have near infrared data. You only have near infrared data and then an optical one. So that's where you can get an accurate photo Z, where the Lyman break happens. And then everything below that, it's very hard to tell.
Okay, thanks.
So thank you for the presentation. Thanks everyone who participated on the session today. So this was our last speaker for today. Caroline, do we have announcements?
Maybe just that tomorrow we will start 1 hour later than today. So 4 p.m. or 1600 UTC with for the simulation geared session. And I think Sambit is gonna kick it off. So stay tuned for that.
Great. So thanks a lot, everyone, for all of the speakers and everyone who participated. And we see you tomorrow.
Thank you. Bye.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Thank you. Bye.
Will, should we stop the stream?